Hello there and welcome to Physics with William, where science slows down, the universe softens around the edges, and even the strangest ideas are allowed to settle gently in the mind before sleep. Tonight, we are stepping into one of the most misunderstood corners of science, a place where order and disorder seem to lean close together, where tiny changes can grow into enormous consequences, and where the world begins to feel less like a machine with neat little gears and more like a living system that keeps surprising itself. Tonight's quiet journey is about chaos theory. Now, chaos is a word we use all the time, usually when something has gone wrong. A kitchen after cooking dinner, a desk covered in papers, a group chat that suddenly has 70 unread messages. The word makes us think of confusion, noise, mess, unpredictability, and perhaps one sock that has somehow vanished into another dimension. But in science, chaos does not simply mean disorder. It does not mean that anything can happen for no reason. It means something subtler and in some ways much more interesting. Chaos theory is the study of systems that follow rules but are still incredibly hard to predict. Not because there are no patterns, but because the patterns are so sensitive, so finely balanced, that the smallest difference at the beginning can completely change what happens later. That is the strange heart of it. Chaos is not the absence of order. It is order that is too delicate to handle casually. Before we wander too far into that thought, I would love to ask you something simple. Where are you listening from tonight? Are you somewhere quiet with the room dim and the day finally loosening its grip? Are you lying in bed, walking slowly through evening thoughts, or sitting somewhere with a cup of tea that has gone slightly colder than you meant it to? And if you feel like answering, what small thing changed the shape of your day today? Maybe a message arrived at just the right moment. Maybe rain started earlier than expected. Maybe you took a different route home and saw something you would have missed. Little changes, tiny details, small bends in the path. They may seem ordinary, but as chaos theory will gently remind us, ordinary things are sometimes where the universe hides its most surprising lessons. And if you find this kind of science soothing, if it helps your thoughts slow down and gives your mind somewhere calm to wander, then a like or a subscription would mean a great deal. It helps this quiet place reach more people who may also be looking for a soft landing at the end of a long day. No pressure, of course. Chaos theory itself might suggest that even one tiny click could create a long chain of consequences, though I promise not to blame you for the entire future of the internet. So, settle in, let your shoulders drop, and allow the idea of chaos to become a little less sharp and a little more curious. Because tonight, we are not going to treat chaos as a storm of nonsense. We are going to treat it as a hidden kind of structure, a strange music inside movement, a science of how simple things can become beautifully difficult to predict. Imagine a quiet morning. Nothing dramatic. The sun is coming through the window. A cup sits near the edge of a table. Somewhere outside, a branch moves slightly in the wind. The day seems ordinary enough, but it is already full of tiny uncertainties. The cup is not exactly where it was yesterday. The air is not moving in exactly the same way. Your hand reaches for the cup with a slightly different angle, because you slept a little differently, because you woke a little earlier, because perhaps a sound outside pulled you from a dream at the wrong moment. Most of the time, nothing much happens. You pick up the cup, you drink your tea. Life continues, but sometimes that tiny difference matters. Your finger touches the handle a little too lightly. The cup shifts. It wobbles once, then twice. It falls, and suddenly the quiet morning has become a small disaster, involving hot tea, a towel, and the deep emotional question of whether the carpet will ever forgive you. No one would say the falling cup was random in a magical sense. It followed gravity. It followed motion. It followed the shape of the table, the movement of your hand, the tilt of the cup, and the smoothness of the surface. Everything obeyed rules. Yet if we tried to predict the exact path of every drop of tea as it splashed across the floor, we would quickly find ourselves in trouble. That is the kind of trouble chaos theory loves. It asks why systems that obey laws can still behave in ways that seem unpredictable. It asks why a tiny difference in the beginning can become a huge difference later. It asks why the weather can be modelled, studied, measured, and watched by satellites, and yet still surprise us. It asks why a dripping tap can fall into a rhythm, then suddenly lose that rhythm. It asks why traffic sometimes slows for no obvious reason, why populations of animals rise and fall in strange cycles, why a heart can beat with orderly variation, and why nature so often produces patterns that look both familiar and impossible to fully repeat. At first, this can feel unsettling. We like to imagine that if we knew enough, we could predict everything. If we knew the exact position of every cloud, every gust of air, every warm current rising from a road, every cool breath slipping down from a hill, then surely we could say exactly what the weather would do next week. If we knew every detail of a swinging pendulum, every push, every angle, every tiny bit of friction, then surely we could know exactly where it would be at every future moment. This dream of perfect prediction is very old. It belongs to the part of the human mind that wants the universe to be a grand clock, ticking forward with total obedience, never hiding a thing. And to be fair, that dream works beautifully in many places. If you drop a spoon, it falls. If you roll a ball across a flat floor, it slows down. If the moon moves around Earth, we can calculate eclipses with astonishing precision. Much of physics has shown us that the universe is not a jumble of accidents. It has regularities, it has laws, it has dependable habits. It is not chaos in the ordinary sense of the word. But then there are systems where the clockwork picture begins to tremble, not because the laws fail, but because the systems become too sensitive. The smallest uncertainty at the start grows and grows until prediction begins to fall apart. It is not that the future has no connection to the present. It is that the connection becomes so tangled that even a tiny error in measurement can become enormous over time. Think of trying to balance a pencil on its tip. For one brief moment, perhaps it stands almost still, but not perfectly still. There is always the tiniest lean, the faintest vibration, the smallest breath in the room. That small difference decides which way the pencil falls. If you could set it up exactly the same way again, with the same motion, the same air, the same surface, then it would fall the same way. But in real life, exact sameness is not something the world easily gives us. A tiny difference sneaks in, and the ending changes. Chaos theory lives in that difference. It does not tell us that the world is meaningless. It tells us that meaning and predictability are not the same thing. A thing can follow rules and still surprise us. A thing can have causes and still be impossible to forecast in detail. A thing can be shaped by order and still look wild. This is why chaos theory is so often connected with the famous idea of the butterfly effect. You have probably heard some version of it. A butterfly flaps its wings in one part of the world, and much later, a storm forms somewhere else. Now, the point is not that butterflies are secretly running the weather, though one imagines they would be very elegant about it. The point is that in a sensitive system like the atmosphere, tiny disturbances can grow. Air is always moving, warming, cooling, rising, falling, twisting and mixing. A small change can alter another change, which alters another, and after enough time, the whole pattern can become different. This is why long-range weather prediction is so difficult. Not because meteorologists are guessing, and not because the atmosphere has no rules. The atmosphere follows physics every moment, but it is enormous, restless and sensitive. To predict it perfectly, we would need perfect measurements of everything that matters, everywhere, all at once. And perfect measurements are not really something humans get to keep in their pockets. We can measure wonderfully well, and our forecasts have become incredibly useful, but chaos places a limit on how far exact prediction can go. There is something humbling in that. The universe is not refusing to be understood. It is simply reminding us that understanding and control are different things. You can understand a river, but that does not mean you can predict the path of every swirl around every stone. You can understand fire, but that does not mean you can know the exact shape of every flame. You can understand a crowd, but that does not mean you can predict the precise footsteps of every person leaving a stadium. In each case, the broad behaviour may be clear. Water flows downhill, fire rises and spreads, people move toward exits, but the fine details become rich, sensitive, and difficult. Chaos theory gives us a way to study that richness without dismissing it as mere mess. And perhaps this is why the subject feels so strangely close to ordinary life. We may not spend our evenings calculating the future of weather systems, but we know what it feels like when small things matter. A missed train changes a conversation changes a decision changes a job, a friendship, a home, a life. You turn left instead of right. You answer the phone instead of letting it ring. You leave 5 minutes later and meet someone you would never have seen. We should be careful, of course, not to turn chaos theory into fortune-telling. It is a science, not a mystical shortcut. But there is a gentle emotional truth nearby. Our lives, like many systems in nature, are made of chains of cause and effect so complex that we often only understand them after they have happened. Looking backward, things can seem almost inevitable. Of course that led to this. Of course that moment mattered. Of course that small decision opened that door. But looking forward, we are inside the system, not above it. We cannot see every thread. We cannot measure every breeze. We live in the unfolding. That may sound uncertain, but it is not necessarily bleak. There is room in it for softness. If the future is sensitive, then small good things may matter too. A kind word, a patient pause, an hour of rest, a small decision to begin again. These are not dramatic events, but they can become part of larger patterns. Sometimes stability begins as quietly as disturbance does. In nature, chaos and stability are often closer than they appear. A heartbeat, for example, is not perfectly regular like a machine. A healthy heart has subtle variation. It speeds and slows in response to breath, movement, emotion, and the needs of the body. Too much irregularity can be dangerous, but too much rigid regularity can also be a sign of trouble. Life often lives between perfect order and total disorder. It needs flexibility. It needs response. It needs the ability to adjust. This is one of the most beautiful surprises of chaos theory. It does not simply show us wildness. It shows us how complexity can arise from simple rules, how patterns can appear without being planned, how systems can hover between predictability and surprise. The branching of trees, the shape of coastlines, the movement of clouds, the flicker of flames, the rise and fall of populations, even the rhythms inside our bodies all carry hints of this deeper idea. Nature is not always smooth and simple. It is often rough, layered, folded, and sensitive. A coastline, for instance, looks simple from far away. You can trace it on a map and say, there is the edge between land and sea. But walk closer, and the edge becomes more complicated. There are bays, stones, pools, cracks, grains of sand, tiny curves inside larger curves. The closer you look, the more detail appears. Some patterns in nature have this quality, repeating at different scales, not perfectly but recognizably. Later, we will call these patterns fractals, and they are one of the places where chaos theory becomes almost visible, not as an equation, but as a shape, a fern leaf, a lightning bolt, a river network, a snowflake, the veins in your hand. They all seem to whisper that nature enjoys repeating an idea with endless little variations. But before we get there, it helps to settle into the basic feeling of chaos theory. It is not about giving up on prediction. It is about understanding the limits of prediction. It is not about saying the universe is random. It is about seeing that some kinds of order are too sensitive to be easily forecast. It is not about replacing science with mystery. It is about making science honest enough to include mystery where it truly belongs, that honesty matters. For a long time, science was often imagined as a path toward perfect certainty. Measure enough, calculate enough, and the future would open like a book. Chaos theory did not destroy that dream all at once, but it did make the pages flutter. It showed that even in simple systems, even with clear rules, there may be practical limits to what can be known. A tiny rounding error, a tiny missed detail, a tiny uncertainty at the start can become the difference between one future and another. And yet, the strange comfort is that chaos itself can have patterns. It can gather around shapes. It can move within boundaries. It can create rhythms that are never exactly repeated, but never completely meaningless either. A chaotic system may not do the same thing twice, but it may still remain within a certain kind of behaviour, as if wandering through an invisible landscape. It is not a coin toss, it is more like a restless path through a hidden valley. That is why the phrase chaos theory can be misleading. It sounds like a theory of everything falling apart. But often, it is a theory of how things hold together while still changing. It is about movement that is structured but never dull. It's about systems that are lawful but not easily tamed. It is about the universe reminding us that it can be both understandable and surprising at the same time. And maybe that is why chaos theory has travelled so far beyond mathematics and physics. People use it when they talk about climate, biology, economics, ecosystems, traffic, technology, and the nervous system. Sometimes they use it too loosely as a fancy way of saying everything is complicated. But at its best, chaos theory gives us a sharper idea than that. It shows how complexity can come from simplicity, how unpredictability can come from rules, and how small beginnings can grow into large consequences. For a sleep science journey, there is something fitting about this topic. As you lie still, the world does not become less complex. Your breathing continues, your heart adjusts. Your brain shifts through waves of activity. Outside, air moves around buildings and trees. Far away, weather systems gather and unwind. The planet turns. The moon pulls softly at oceans. Everything is in motion, and yet here, in this small pocket of night, there can still be calm. Perhaps calm is not the absence of motion. Perhaps it is simply a pattern gentle enough for the mind to rest inside. So tonight, as we begin, let chaos become less like noise and more like a door. Behind that door is a different way of seeing the world. Not as a place where everything can be predicted perfectly, and not as a place where nothing makes sense, but as a place where rules and surprise live side by side. A place where a tiny change can matter, where patterns can hide inside disorder, and where the universe can be lawful without being boring. And to understand how this idea took hold, we need to begin with the old dream it disturbed, the dream of a perfectly ordered universe. A universe of clean motions, steady causes, and predictable futures. For a while, that dream seemed almost complete. The planets moved, clocks ticked, pendulums swung, and science appeared to be building a world where everything could one day be known in advance. But even in the quiet confidence of that ordered picture, small tremors were waiting. For a long time, one of the most comforting dreams in science was the idea that nature was, underneath all its noise and weather and spilled tea, perfectly ordered. Not merely sensible in a broad way, but deeply predictable. If a stone fell, there was a reason. If a planet moved, there was a path. If a pendulum swung, there was a rhythm. The universe, in this older picture, was like a grand clock with hidden wheels. Some wheels were large enough to see, like the motion of the moon. Some were far too small, like the movement of air or the vibration of atoms. But the hope was that every wheel turned according to laws, and if we could only understand those laws well enough, we could know exactly what would happen next. It is worth pausing here, because this dream was not foolish. It was not a childish wish that science later threw away. It worked. It worked so well that it changed civilization. The motion of planets could be described. Eclipses could be predicted. Cannonballs, tides, falling apples, swinging clocks, and the paths of ships could all be brought into one expanding picture of cause and effect. For anyone living through the rise of classical physics, the universe must have seemed suddenly less like a place ruled by moods and mysteries, and more like a place with instructions written into its bones. You did not need to beg the sky to explain itself. You could observe, measure, think carefully, and the sky would begin to answer. This way of seeing nature reached one of its great forms in the work of Isaac Newton. Newton gave physics a language for motion, force, and gravity that was so successful it became almost impossible to imagine nature any other way. In Newton's universe, if you knew where something was, how fast it was moving, and what forces were acting on it, then in principle you could calculate its future. A planet did not wander because it felt like wandering. A falling stone did not make a choice. The world moved according to rules, and those rules were precise. This was a powerful idea, and it still is. When you toss a ball gently into the air, you do not expect it to pause thoughtfully and turn into a pigeon. It rises, slows, falls, and lands. When you slide a book across a table, it does not suddenly drift upward and begin a career in aviation. It slows because friction acts on it. Everyday motion has a dependable quality. Even if you are not doing formal physics, your body understands this. You catch falling cups, dodge rolling objects, and step over puddles, because somewhere inside you is a very practical little physicist, doing rough calculations while pretending not to be smug about it. For simple situations, prediction can be wonderfully accurate. A pendulum swinging through a small arc behaves with a calm regularity. A planet orbiting the sun follows a path that can be predicted over long stretches of time. A clock, if it is well made and not quietly plotting against you, ticks in a steady rhythm. These systems encourage the belief that uncertainty was mainly a problem of ignorance. If we failed to predict something, perhaps we simply did not know enough. If the weather surprised us, perhaps we needed better measurements. If a system behaved oddly, perhaps there was some hidden detail we had not yet included. That belief produced a famous thought experiment. Imagine a mind so vast that it knew the position and motion of every particle in the universe. Imagine it knew every force, every interaction, every detail of the present moment. Such a mind, it was argued, could calculate both the future and the past with perfect certainty. Nothing would be uncertain to it. The fall of a leaf, the motion of a star, the sneeze of a cat at breakfast, all would be part of one immense chain of necessity. To us, life would feel open and surprising. To this imaginary intelligence, the whole story would already be readable. It is a dramatic idea, and also slightly rude. No one likes the thought that even their most spontaneous decision to have a biscuit was predictable from the beginning of time. Still, the idea captured something important about classical order. If the laws are precise and the starting conditions are known perfectly, then the future should follow exactly. Uncertainty, in this view, belongs to us, not to nature. Nature knows what it is doing. We are the ones squinting at it through foggy spectacles. For many systems, this attitude remains useful. Engineers rely on it. Astronomers rely on it. Every bridge, aircraft, satellite, and carefully timed traffic light contains some trust in the orderly behaviour of the physical world. If reality were pure nonsense, we would not have elevators, clocks, or toast that usually lands in a disappointingly predictable way. Science did not abandon order. It still depends on order every day. But order began to tremble when scientists looked more carefully at systems that were still lawful, still mechanical, still obedient to physics, but not so easily predicted. These were not magical systems. They did not break the rules. They followed the rules so faithfully that the surprise came from the rules themselves. A simple example begins with something very ordinary, a pendulum. A single pendulum is one of the great icons of regular motion. It swings left and right with a soothing rhythm, which is why clocks loved it for so long. But now imagine a pendulum attached to another pendulum. One arm swings from a fixed point, and another arm swings from the end of the first. You might expect a slightly more complicated version of the same gentle motion. A little wobblier, perhaps, a little less elegant, like a dancer who's had too much coffee. Instead, the motion can become wildly unpredictable. The double pendulum may swing smoothly for a moment, then flip over, twist, reverse, and wander through shapes that seem almost impossible to guess in advance. Nothing supernatural is happening. Gravity is still gravity. Motion is still motion. The arms are still connected. Yet a tiny difference in the starting position can lead to a completely different path after only a short time. Start it almost the same way twice, and soon the two motions can look unrelated, as if the second pendulum has developed a private opinion about life. This is where the older dream starts to shake. The system is simple, the rules are clear. There are only a few moving parts, and still, exact long-term prediction becomes difficult. Not because the system has no order, but because the order is sensitive. A tiny change at the start does not remain tiny. It grows. That growth is one of the central ideas of chaos theory. In an ordinary stable system, small errors often stay small or fade away. If you gently nudge a hanging pendulum, it may swing a bit differently, but the overall behavior remains familiar. If you make a small mistake when estimating where a rolling ball will be a moment later, the mistake may not explode into catastrophe. You can correct it. You can keep up. Stable systems are forgiving. They allow a little imprecision. Chaotic systems are less forgiving. A small uncertainty in the starting point may double, then double again, then keep growing until prediction loses its grip. This does not mean the system is random. If you could repeat the starting conditions exactly, the system would repeat exactly. But exact repetition is not something nature hands over easily. Every measurement has limits. Every surface has tiny differences. Every breath of air shifts something. And in a chaotic system, those tiny differences matter. The trouble is not only that humans are clumsy measurers, even our best instruments have boundaries. To predict a chaotic system far into the future, we would need to know its starting state with impossible precision. Not just fairly well, not just very well. We would need details beyond anything physically practical. And if one small part is slightly wrong, the prediction begins to drift. At first, the drift may be invisible, then it becomes noticeable, then it becomes everything. Weather is the most famous example, and for good reason. The atmosphere surrounds the planet in a restless ocean of air. It is heated by the sun, cooled by space, stirred by oceans, shaped by mountains, turned by Earth's rotation, and constantly affected by moisture, pressure, temperature, and motion. It is not a simple machine with a few neat levers. It is an enormous moving system, and every part talks to other parts. Warm air rises and changes pressure. Pressure changes wind. Wind moves moisture. Moisture forms clouds. Clouds change sunlight. Sunlight changes temperature. Around and around it goes, like a conversation where everyone is speaking at once and one cloud keeps interrupting. The atmosphere obeys physics. It is not careless. But because it is chaotic, tiny differences in measurement can grow into large differences in outcome. This is why weather forecasts are often good over the next few days, less certain after that, and much less certain farther out. There is a horizon beyond which the fine details become too sensitive to predict exactly. We can still understand climate patterns, seasonal tendencies, and broad conditions, but the precise weather on a particular street at a particular hour far in the future becomes another matter. This distinction is important. Chaos theory does not say that because the weather is chaotic, nothing can be known. That would be like saying that because soup is complicated, lunch is impossible. We can know a great deal. We can forecast with skill. We can understand patterns. We can issue warnings, track storms, and model large-scale behavior. But chaos tells us there are limits to exactness. The universe may be lawful without being fully predictable in every detail. One of the early scientific surprises came when researchers used computers to simulate weather. Computers were supposed to make predictions stronger, and they did. But they also revealed something strange. Very tiny differences in the numbers entered at the beginning could lead to very different results later. At first, this seemed like a mistake. Surely a small rounding difference should only produce a small difference in the answer. That is what common sense expects. If you start almost in the same place, you should end almost in the same place. But chaotic systems do not always respect common sense. The almost same beginning can unfold into a very different future. The computer was not failing. It was showing something real about the mathematics of the system. The atmosphere had a kind of sensitive dependence. The seed of the future was in the present, yes, but the seed was so delicate that even the smallest disturbance could change the shape of the tree. This is the point where order begins to look less like a straight line and more like a branching path. In older clockwork thinking, a cause leads neatly to an effect, and that effect leads neatly to another. But in chaotic systems, causes are tangled across many scales. A tiny movement affects a larger pattern. The larger pattern changes the environment for the tiny movement. Everything feeds back into everything else. The result is not simple disorder. It is complex order with loops. Feedback is one of those plain words that hides a powerful idea. A feedback loop happens when the result of a process affects the process itself. Imagine a microphone placed too close to a speaker. A small sound enters the microphone, comes out of the speaker louder, re-enters the microphone, comes out louder again, and suddenly everyone in the room is making the same unhappy face. That squeal is a simple example of feedback. Something small gets amplified because the system feeds its own output back into its input. Nature is full of feedback. Ice reflects sunlight, which affects temperature, which affects ice. Plants change moisture and temperature around them, which affects how plants grow. Predator populations affect prey populations, which then affect predator populations. The heart responds to the body, and the body responds to the heart. Your brain reacts to stress, and the stress reaction can produce more signals that the brain must handle. Even daily habits contain feedback. Sleep affects mood, mood affects choices, choices affect sleep. And somewhere in that loop, a person may find themselves eating cereal at midnight and calling it a reasonable strategy. In systems with feedback, behavior can become rich very quickly. A small change is not simply passed along. It may be amplified, delayed, reduced, reversed, or transformed. The future is not just a straight continuation of the present. It is the result of many interactions folding back on themselves. This is why some simple rules can create surprisingly complex outcomes. You do not always need a complicated rule to get complicated behavior. Sometimes, a rule repeated over and over is enough. A small process can generate cycles. A cycle can become unstable. Instability can lead to chaos. The system may move from calm to periodic behavior, then to a more complicated rhythm, then to motion that never quite repeats. All without adding magic, hidden spirits, or a tiny gremlin adjusting the settings from behind the curtain. That transition from order to chaos is one of the most fascinating things scientists study. A system may begin in a stable state. Push it gently and it returns to balance. Push it more and it begins to oscillate. Push it further and the rhythm may split into a more complex rhythm. Keep changing the conditions and eventually the system can enter chaos. The order does not vanish all at once. It trembles, wavers, doubles, tangles, and then becomes something harder to predict. You can see hints of this in flowing water. A slow stream moves smoothly, almost like glass. Increase the speed, and ripples appear. Increase it further, and swirls form around stones. At higher speeds, the flow becomes turbulent, full of eddies and curls that rise and vanish. The water is still obeying physical laws. Every molecule is following interactions, but the visible motion becomes too complicated to predict in exact detail. A smooth flow becomes a restless one. The same idea appears in smoke rising from a candle. Close to the flame, the smoke may rise in a thin, smooth column. A little higher, it wavers. Then the column breaks into curling shapes, twisting and mixing with the air. It looks almost alive. If you tried to predict the exact curl of smoke a few seconds later, you would quickly understand why nature keeps physicists humble. The smoke is not random in the sense of having no cause. It is sensitive, interacting, and unstable. Order trembles when stability gives way to sensitivity. That phrase sounds grand, but the experience is familiar. Think of traffic on a busy road. Cars move steadily for a while, then one driver brakes slightly. The car behind brakes a bit more, the next driver reacts later and brakes harder. Soon, a wave of slowing travels backward through the traffic, even though there may be no crash, no roadwork, and no obvious reason. A tiny disturbance becomes a traffic jam. Everyone eventually creeps along, wondering what happened, and the answer is something deeply unsatisfying. Almost nothing happened, and yet that was enough. Crowds can behave similarly. A small hesitation at a doorway can grow into a bottleneck. A small movement in one part of a crowd can ripple outward. Markets, ecosystems, power grids, social networks, and even conversations can show versions of the same principle. When many parts interact, and when the output of one part becomes the input for another, small events can grow. This does not mean every small event becomes important. Most small changes disappear. A butterfly wing does not always make a storm. A tiny noise does not always become a song. A small mistake does not always change a life. Chaos theory is not saying that every detail is secretly destiny. It is saying that in certain systems, under certain conditions, small differences can be amplified in ways that make long-term prediction difficult. That careful wording matters. Chaos theory is sometimes turned into a dramatic slogan, as if any tiny action can automatically reshape the universe. The real science is more precise and more interesting. Sensitivity depends on the system. Some systems damp disturbances, some amplify them, some are stable in one range and chaotic in another. A cup sitting in the middle of a table is usually stable enough. A cup balanced halfway over the edge is waiting for trouble. Conditions matter. The older dream of perfect order did not disappear because chaos showed nature to be lawless. It trembled because chaos showed that laws do not guarantee practical predictability. You can know the rules and still be unable to follow every detail into the future. You can understand the system and still be surprised by it. This is not failure. It is a deeper kind of understanding. There is a quiet lesson here about control. Human beings like control. We schedule, plan, measure, forecast, and label. We build calendars and alarms. We check maps before leaving the house and still somehow arrive late because one road decided to become philosophical. Much of life is an attempt to reduce uncertainty, and that is reasonable. But chaos theory reminds us that some uncertainty is not merely a gap in our effort. It is built into the behavior of complex systems, not because they are beyond science, but because science itself tells us where prediction has limits, and yet, limits can be useful. Once we know a system is chaotic, we stop asking it the wrong questions. We stop demanding exact long-term detail when the system cannot provide it. Instead, we ask about patterns, ranges, probabilities, boundaries, and tendencies. We learn to forecast in a different way. We learn to look for structure inside unpredictability. This shift is subtle but important. In a perfectly predictable system, the goal is to know the future state exactly. In a chaotic system, the goal may be to understand the shape of possible futures. What kind of behavior is likely? What conditions lead to stability? What changes increase risk? What patterns keep returning? The question becomes less like asking where one leaf in a river will be days from now, and more like asking how the river flows, where it speeds up, where it swirls, and where a leaf is likely to travel. That is not a weaker kind of science. It is a science adapted to a richer world. The trembling of order also changed the way scientists thought about simplicity. Before chaos theory, it was tempting to assume that simple causes produce simple effects, and complex effects required complex causes. But chaotic systems broke that expectation. A very simple system could produce motion that looked wildly complex. A short rule, repeated again and again, could create patterns no one expected. Nature did not need to be complicated at the foundation in order to become complicated in appearance. Complexity could grow naturally from repetition, feedback, and sensitivity. This idea opened a door between physics, biology, mathematics, and everyday life. Suddenly, the same kind of thinking could help describe a dripping tap, a heart rhythm, a population of animals, the spread of forest fires, the branching of blood vessels, the movement of planets in more complicated arrangements, and the shape of clouds. Different systems, different materials, different scales, but similar patterns of sensitivity and feedback. Chaos theory became a language for noticing family resemblances across nature. There is something pleasing about that. The world is not just a collection of separate facts, it has recurring habits. A swirl of cream in coffee, a storm in the atmosphere, and a spiral in a galaxy are not the same thing, but the mind notices echoes, flow, rotation, instability, pattern. Science becomes a way of listening carefully to those echoes without forcing them to mean more than they do. So when order begins to tremble, it is not the end of understanding, it is the beginning of a more flexible understanding. The universe is still lawful, but not always tame. It is still patterned, but not always simple. It can be stable, rhythmic, sensitive, or chaotic depending on the conditions. A pendulum can swing calmly or flip wildly. Water can flow smoothly or break into turbulence. Weather can follow physical laws and still refuse to give us every detail far in advance. And perhaps, as we sit with this idea, chaos becomes less alarming. It is not a monster hiding under the bed. It is more like a reminder that the bed itself is made of atoms. The room is full of air currents, your body is full of rhythms, and the world has always been more alive with interaction than it first appears. Order is real. So is instability. They are not enemies, they are neighbours. The first great shock of chaos theory was not that nature could be messy. Everyone already knew that. The shock was that messiness could arise from order, that unpredictability could arise from rules, and that a system could be completely deterministic in principle, while still impossible to predict in practice. That idea changed the meaning of prediction. It changed the meaning of certainty. And it prepared the way for one of the most famous images in all of science. A small wing beat in one place, and a weather pattern somewhere else beginning ever so slightly to change. The image of a butterfly changing the weather is one of those scientific ideas that escaped the laboratory and learned how to live in everyday speech. It appears in films, novels, conversations, and those slightly dramatic moments when someone says that missing one bus may have changed the entire course of their life. It is easy to see why the image stayed with us. A butterfly is almost absurdly delicate. A storm is enormous. Put them in the same sentence, and the mind naturally leans closer. Surely something so small cannot matter to something so large. Surely the atmosphere is too vast to care about one tiny flutter of wings. And yet, chaos theory asks us to be careful with the word surely. The butterfly effect does not mean that one butterfly literally creates a hurricane as if it has a private weather control system tucked under its wings. It does not mean that every tiny event becomes enormous. It does not mean the world is ruled by magical accidents. The real idea is more precise and in its own way more unsettling. In certain systems, very small differences at the beginning can grow into very large differences later. The atmosphere is one of those systems. It is sensitive, it is connected, it is restless, it is always carrying forward the memory of small changes, mixing them into large emotions until the future becomes difficult to separate from the tiniest details of the present. The story begins not with a butterfly, but with weather prediction, computers, and a scientist named Edward Lorenz. Lorenz was a meteorologist and mathematician, and he was interested in using computers to model the atmosphere. Today, that sounds ordinary. Weather forecasts now depend on enormous computer models, satellite observations, ocean data, radar, and a constant flow of measurements from across the planet. But in the middle of the 20th century, the idea of simulating weather with a computer still had a sense of frontier about it. Computers were new, limited, slow by modern standards, and not exactly the sleek, quiet machines we keep in our pockets. They were more like large, humming cabinets, with the personality of a stubborn refrigerator. Lorenz was working with a simplified weather model. It was not the whole atmosphere in full detail. No model could handle that at the time, and even today models must simplify. His system used numbers to represent changing atmospheric conditions. The computer would take the numbers, process them step by step, and produce a forecast of how the system would evolve. It was a toy atmosphere in a sense, a small mathematical weather world living inside a machine. One day, Lorenz wanted to repeat part of a previous simulation. Instead of starting from the beginning, he entered numbers from an earlier printout and let the computer continue. At first, the new run seemed to match the old one. The paths were close. The system behaved as expected. But then, after more time passed, the new result drifted away. Then it drifted more. Soon it looked nothing like the original. It was as if the computer had taken the same weather and quietly led it into a different universe. At first glance, this looked like a mistake. Perhaps the machine had malfunctioned. Perhaps the numbers had been entered incorrectly. Perhaps the computer, like many machines, had simply decided to be difficult because it was Tuesday. But Lorenz eventually realized what had happened. The numbers he entered from the printout were not exactly the same as the numbers stored inside the computer. The printout rounded them. The difference was tiny, so tiny that in an ordinary calculation one might expect it to be harmless. A small rounding difference should lead to a small difference in the result. That is the common sense expectation. But the model did not behave that way. The tiny difference grew. It did not merely stay as a small correction. It spread through the system, step by step, changing the future of the simulation until the two forecasts no longer resembled each other. This was the weather refusing to behave like a neat clock. What Lorenz had found was sensitive dependence on initial conditions. That phrase sounds technical, but the meaning is simple enough to hold in the hand. Initial conditions are the starting details of a system. Sensitive dependence means that small changes in those starting details can produce large changes later. Not always immediately, not always dramatically at first. But over time, in a chaotic system, the difference can grow until prediction becomes unreliable. The weather is a perfect place for this to happen because the atmosphere is not one thing moving in one simple direction. It is a planet-wide ocean of air full of interacting motions. It is warmed by sunlight, cooled by night, stirred by oceans, interrupted by mountains, twisted by Earth's rotation, moistened by evaporation, and shaped by countless local details. A warm field, a cold lake, a patch of cloud, a city releasing heat, a forest holding moisture, a storm forming over the sea, all of these details matter. The atmosphere is not merely big, it is connected across scales. Small motions can feed into larger motions, and larger motions can reshape smaller ones. If you have ever watched cream swirl into coffee, you have seen a tiny household version of this kind of complexity. At first, the cream enters as a pale ribbon. It curls, folds, stretches, and twists. A gentle stir creates spirals within spirals, shapes that look almost planned and yet are never exactly repeated. If you tried to predict the exact path of one tiny part of that cream, you would soon be defeated by the details. The liquid is following physical rules. Nothing lawless is happening. But the pattern becomes so folded and sensitive that exact prediction slips away. The atmosphere is like that, except the coffee cup is Earth. The cream is heat and moisture and pressure, and the spoon is everything from sunlight to ocean currents to mountains to the turning of the planet. Also, the cup has no lid, which is very inconsiderate. This is why the butterfly effect became such a powerful metaphor. It gives us a way to imagine sensitive dependence. A butterfly flaps its wings. That movement creates a tiny disturbance in the air. Most of the time, that disturbance may fade into the background. But in a system as sensitive and interconnected as the atmosphere, under the right conditions, tiny disturbances can be amplified. They can shift air slightly, which shifts other air, which changes pressure somewhere else, which changes the timing of a forming system, which changes where moisture collects, which changes how a storm develops. The butterfly is not the cause in the simple way a match causes a flame. It is one small part of an immense web of causes. That distinction matters. Chaos theory does not say small things always dominate large things. If that were true, weather would be completely hopeless, and umbrellas would become philosophical objects rather than practical ones. Many small disturbances vanish. They're absorbed, smoothed out, or overwhelmed. But some systems, at some moments, are poised in such a way that small differences can change the path ahead. The butterfly effect is about possibility in sensitive systems, not guaranteed drama in every breeze. Weather forecasting is a constant negotiation with this sensitivity. To forecast the weather, scientists begin by observing the current state of the atmosphere. They measure temperature, pressure, humidity, wind speed, wind direction, cloud cover, sea surface temperature, and many other things. They gather data from satellites, aircraft, buoys, weather balloons, radar stations, ships, and ground-based instruments. All of this information is used to estimate what the atmosphere is doing right now. Then computer models apply physical laws to calculate how that state may evolve. The problem is that the current state can never be known perfectly. We do not have measurements at every point in the atmosphere. We do not know the exact temperature of every pocket of air, the exact motion of every swirl, the exact water content of every cloud droplet. Even if we had far more instruments, there would still be limits. Measurements have precision. Data has gaps. The atmosphere changes while we're measuring it. The present is not a still photograph waiting politely for us to finish. In a non-chaotic system, small uncertainties might not matter much, but in weather, they can grow. A tiny uncertainty in the starting point can become a noticeable uncertainty in tomorrow's forecast, then a larger uncertainty several days later, then a very large uncertainty further on. That is why forecasts tend to be more reliable in the near future and less certain as the days stretch ahead. It is not because meteorologists are careless, quite the opposite. It is because the atmosphere is a chaotic system, and chaos places a natural limit on exact prediction. This is sometimes called a prediction horizon. It is the distance into the future beyond which detailed forecasts lose their reliability. For weather, this horizon is not fixed like a wall. It depends on the situation. Some weather patterns are more stable and easier to forecast. Others are more sensitive and difficult. A large, slow-moving, high-pressure system may be fairly predictable for a while. A developing storm in a complicated environment may be much harder. The atmosphere has moods, though scientists prefer not to call them that because it makes the atmosphere sound like it is ignoring texts. Modern forecasts are much better than they used to be. This is important to say, because chaos theory is sometimes misunderstood as a reason to shrug and give up. In reality, weather prediction has improved enormously. Better observations, better computers, better models, and better understanding have all made forecasts more accurate. We can track hurricanes, anticipate cold fronts, predict heat waves, and warn people about dangerous storms in ways that save lives. Chaos does not make forecasting impossible. It makes forecasting a careful, limited, probabilistic art built on serious science. One of the most useful tools in modern forecasting is the ensemble forecast. Instead of running one model once and pretending that one answer is perfect, Meteorologists run many versions of a forecast with slightly different starting conditions or model assumptions. If all the versions produce similar outcomes, confidence is higher. If they spread apart, uncertainty is greater. This is, in a way, a direct response to the butterfly effect. Since tiny differences can grow, scientists deliberately explore how those tiny differences might change the future. They do not ignore sensitivity. They invite it into the room, give it a chair, and ask it to please behave long enough to be studied. Imagine releasing several leaves into a river at almost the same place. If the river is slow and smooth, the leaves may drift together for a long time. If the river is turbulent, some leaves may catch small currents, some may spin into eddies, and some may move quickly away. Watching the spread of the leaves tells you something about the river. Ensemble forecasting does something similar with possible weather futures. It shows not just one path, but a family of paths. That shift from single certainty to a range of possibilities is one of the practical gifts of chaos theory. It teaches us not only to ask what will happen, but how confident we can be, and how different the future might become if the starting point is slightly different. This does not make the forecast weaker. It makes it more honest. A forecast that says rain is possible with a certain level of confidence is often more useful than a forecast pretending to know the exact mood of every cloud. There is also a difference between weather and climate, and chaos theory helps clarify it. Weather is the day-to-day state of the atmosphere. It is whether it rains tomorrow, whether the wind is strong this evening, whether the sky is clear on your walk home. Climate is the long-term pattern. It is the average behaviour of weather over years, decades, and longer. Weather is like the exact path of one wandering leaf. Climate is the shape and flow of the river. Because weather is chaotic, exact day-to-day prediction far into the future is limited. But that does not mean climate cannot be studied. We may not know whether it will rain on one specific street at one specific hour months from now, but we can understand how energy, greenhouse gases, oceans, ice, and atmospheric circulation affect long-term averages and risks. This distinction is sometimes missed. Chaos in weather does not erase patterns in climate. A dice roll is unpredictable in detail, but the statistics of many rolls can still be understood. Similarly, the precise wiggle of weather may be chaotic, while broader climate trends can still be physically meaningful. The butterfly effect, then, is not an excuse to say everything is unknowable. It is an invitation to know in the right way. The weather teaches this beautifully because it is familiar. We live inside it. We feel it on our skin, we plan around it, complain about it, and occasionally have entire conversations that consist of nothing but observing that it is, indeed, raining again. The atmosphere is one of the few chaotic systems we cannot avoid. It is above us, around us, and sometimes inside our shoes when the forecast said light showers and the sky apparently heard dramatic monsoon. But weather also shows the emotional side of prediction. We want the future to be knowable, because our plans depend on it. We want to know whether to bring a coat, whether a flight will be delayed, whether a storm will pass north or south. We want certainty not because we are unreasonable, but because certainty feels safe. Chaos theory does not remove safety. It asks us to become wiser about uncertainty. It teaches that good prediction includes confidence, limits, and humility. Humility is a recurring theme here. Edward Lorenz did not discover chaos by adding more complexity to weather. He discovered it in a simplified model. That is one of the surprising things. Chaos was not only hiding in enormous systems too complicated to understand. It could appear in small mathematical models with only a few changing quantities. This meant unpredictability was not merely a practical inconvenience caused by having too many details. It was a deep property of certain deterministic systems. The rules could be simple. The outcome could still be impossible to predict exactly after enough time. This realization shook the older view of a perfectly predictable universe. It suggested that even if nature obeys laws, knowing those laws is not always enough. The starting conditions matter with impossible delicacy. A forecast is only as good as the knowledge of the present, and in a chaotic system the present would need to be known with a perfection that reality refuses to provide. There is a strange comfort in this refusal. The universe is not sloppy, it is not broken. It is simply richer than the old clockwork picture allowed. A clock is predictable because its parts are designed to reduce sensitivity. A good clock does not care much about tiny disturbances. It is made to keep a steady rhythm. The atmosphere is not a clock. It is a flowing, heated, rotating, moist, self-interacting ocean of gas wrapped around a planet. It was never built to make our picnic planning easy. And yet within its wildness there is beauty. Weather patterns have shapes. Clouds form towers, sheets, curls and waves. Storms spiral. Fronts sweep across maps. Jet streams bend and loop high above us. Local winds rise and fall with the heating of land and sea. There are rhythms, seasons, cycles and tendencies. Chaos does not remove pattern. It makes pattern dynamic. You can see this if you watch the sky over a long afternoon. At first, the clouds may look still, almost painted. Then you notice slow movement. Edges dissolve. New towers rise. Shadows shift across fields or rooftops. A cloud that was soft and harmless begins to grow taller. Another thins into wisps. The sky is never truly frozen. It is a system in motion, shaped by invisible currents. You're watching physics unfold overhead, not as a neat diagram, but as a living performance that never repeats exactly. The butterfly effect reminds us that the performance has no single simple cause. A storm is not caused by one thing. It is the result of many conditions coming together. Heat, moisture, instability, pressure, wind, geography, timing. Remove one element or shift it slightly, and the storm may form differently, arrive later, weaken, strengthen, or miss a region altogether. Weather is a story written by many authors at once, and some of them have very small handwriting. This way of thinking can feel familiar beyond meteorology. Human situations often have a similar quality. A conversation changes tone because of one sentence. A plan changes because of one delay. A mood shifts because of one memory. Again, we should not confuse life with a weather model, and chaos theory should not be stretched until it becomes a vague philosophy of everything. But it does give us language for sensitivity, feedback, and unfolding consequences. It reminds us that the future is not always a straight road. Sometimes it is a branching system, and small differences near the branch point can matter. Still, there is another side to the butterfly effect that is easy to overlook. If small disturbances can grow, then small uncertainties also grow. This means that prediction is not just about having strong computers. It is about the relationship between information and time. The farther into the future we ask, the more exact our present knowledge must be. In chaotic systems, the demand for precision grows so quickly that eventually it becomes impossible. Not inconvenient, not expensive, impossible in practice. That boundary is not a defeat for science, it is a discovery by science. Knowing what cannot be predicted exactly is itself knowledge. It prevents false confidence. It keeps us from pretending that a single forecast, model or plan can capture every future detail. It encourages flexible thinking. It asks us to prepare for ranges, not just points. In weather, that means probabilities, warnings, and scenarios. In life, perhaps it means leaving a little room in the schedule, carrying the umbrella when the sky looks suspicious, and not assuming the universe has signed a contract to follow your calendar. The story of Lorenz and the butterfly effect also shows how scientific breakthroughs can arrive quietly. There was no thunderclap, no glowing portal opened above the computer. A rounded number produced a surprising result and someone paid attention. That is often how science moves. A detail misbehaves. A result refuses to match expectation. A small error turns out not to be an error at all but a doorway. The weather would not behave, and in refusing to behave it revealed a deeper kind of order. Lorenz later described the idea with the now famous butterfly image, asking whether the flap of a butterfly's wings in one place could set off a tornado somewhere else weeks later. The question was not meant as a literal weather report. It was a poetic way of expressing a mathematical fact. Sensitive dependence means the atmosphere has a long memory for small differences, though that memory becomes mixed, stretched, and folded into larger patterns. A tiny disturbance may be lost, or it may become part of a chain that matters. The difficulty is knowing which tiny details will matter before the future unfolds. And that brings us back to the quiet wonder at the centre of chaos theory. A system can be deterministic, meaning its future follows from its present according to rules and still be unpredictable in practice. This is not a contradiction. It is the whole point. The rule-based nature of the system does not give us unlimited access to its future, because our knowledge of the present is always limited. Between law and prediction lies measurement. Between cause and forecast lies sensitivity. Between order and outcome lies chaos. So the butterfly effect is not really about butterflies. It is about the fragile bridge between now and later. It is about how small differences can be stretched by time. It is about why the atmosphere, despite all our science, still keeps some of its cards face down. It is about how prediction changes when the world is not a rigid machine, but a moving system of loops, flows, amplifications, and interactions. And perhaps, as you listen, you can feel why this idea became so memorable. It is scientific, but it also touches something personal. We know the future is shaped by small things. We know not every small thing matters, but some do. We know that life is not random, and yet it is not fully predictable either. We live in the space between pattern and surprise. We make plans beneath a sky that is still deciding what to do. The weather, in its refusal to behave perfectly, taught science a new humility. It showed that the world can follow rules and still remain open in detail. It showed that prediction has horizons. It showed that tiny differences are not always tiny for long, and it gave us one of the most enduring images in modern science, a delicate wing beat moving through a vast atmosphere, not commanding the storm, but reminding us that in a sensitive world, beginnings matter. From here, the next question comes naturally. If weather can behave this way, if a simplified model can create such surprising results, then how much complexity can arise from rules that are even simpler? How can something with only a few instructions produce patterns that look alive, wild, and almost endless? To answer that, we have to look more closely at the strange power of simple rules repeated over time. There is a quiet surprise at the centre of chaos theory, and it is this. A world does not need complicated instructions in order to become complicated. It does not need an enormous manual, a secret blueprint, or a committee of tiny invisible engineers working late into the night with clipboards. Sometimes, a few simple rules, repeated again and again, are enough to create behaviour so rich that it looks almost impossible. The rules may be plain, the outcome may be wild. This is not how we usually expect things to work. Most of us assume that complex results must come from complex causes. If a machine has many moving parts, then perhaps it needs a long explanation. If a city has roads, buildings, markets, power lines, people, schedules, traffic lights, and that one junction where everyone seems to forget how lanes work, then its complexity feels natural. It has many pieces, so it behaves in complicated ways. But chaos theory, along with the broader study of complex systems, tells us something stranger. Sometimes complexity does not come from a large number of rules. It comes from simple rules interacting with themselves over time. A snowflake is a lovely example to hold in the mind. Each snowflake grows as water vapour freezes into ice around a tiny starting point. The basic rules of ice crystal growth are not emotional. They are not artistic in the human sense. Water molecules attach in ways shaped by temperature, humidity, and the structure of ice. Yet from these physical rules come delicate branching shapes, tiny frozen stars, each one familiar and each one different. The snowflake is not designed petal by petal. It grows, Its beauty is not drawn from a plan but from a process. That word, process, matters. A simple rule repeated over time can become a process, and a process can create a world. Think of a tree. At first, it seems too complex to be explained simply. A trunk rises, branches split, smaller branches split again, leaves spread into the light. No one has gone along measuring each branch and deciding exactly where it should turn. The tree follows growth rules. It grows toward light, it responds to gravity, it transports water, it adds new tissue, it reacts to wind, shade, damage, seasons, and the availability of nutrients. Out of all this comes a shape that is both ordered and unpredictable. You can recognize an oak as an oak, but you cannot predict the exact path of every branch years before it grows. The general form is lawful. The details are wild. The same is true of rivers. A river follows gravity. Water flows downhill. That rule could hardly sound simpler, and yet rivers curve, branch, braid, carve valleys, shift channels, form deltas, and write long wandering signatures across landscapes. The water does not decide to become beautiful. It simply moves, erodes, deposits, responds to obstacles, and repeats its work across time. A river valley is complexity carved by simple physical tendencies, with every stone and slope adding its own quiet suggestion. So when we ask why simple rules can create wild worlds, we are really asking how repetition, interaction, and feedback turn plain beginnings into rich outcomes. A single rule may be easy to understand, but when that rule is applied again and again, especially when the result of one step becomes the starting point for the next, the future can grow quickly beyond easy intuition. A familiar example is the spread of ripples in water. Drop a pebble into a pond and circles move outward. That part is simple and soothing. But now imagine many pebbles dropping at different times. The ripples meet, cross, strengthen each other in some places, weaken each other in others, bounce from the edges, and overlap into shifting patterns. Each ripple follows a rule. The combined surface becomes complex. Nothing mystical has entered the pond, though if you are sitting beside it at dusk with trees reflected in the water, it may still feel slightly enchanted. This is the difference between understanding a rule and knowing every consequence of that rule. The rule can be simple. The consequences can be numerous, layered, and sensitive. In chaos theory, this is especially important because many chaotic systems are deterministic. That means the next state follows from the previous state according to rules. But if those rules involve feedback, sensitivity, or repeated interaction, then the result can become deeply unpredictable in detail. One of the most important discoveries in the study of chaos was that complexity could arise in systems with very few moving parts. You did not need the whole atmosphere to produce surprise. You did not need an entire ocean, forest, or economy. Even a simple mathematical model could begin calmly, then fall into cycles, then split those cycles, then move into chaos. That was startling because it showed that chaos was not merely a problem of too much stuff. It was not just nature being crowded. It was something that could emerge from the structure of the rules themselves. Imagine a population of animals in a small environment. The rule might sound straightforward. If there are few animals and plenty of food, the population grows. If there are too many animals and not enough food, the population shrinks. This is simple enough to explain over breakfast, though perhaps not if the animals are also at the table. But when such a rule is repeated across generations, something interesting can happen. Under some conditions, the population settles into a stable size. Under others, it rises and falls in a steady cycle. Change the conditions further, and the cycle becomes more complicated. Push the system again, and the population may shift in a way that seems irregular, even though the same basic rule is being applied each time. This kind of behaviour is one reason chaos theory became so important. It showed that even simple models of growth and limitation could produce unexpected patterns. The wildness was not added from outside, It was already inside the repeated rule. A dripping tap gives another small but memorable example. At first, drops may fall one after another in a steady rhythm. Plink, plink, plink. Very calm unless you're trying to sleep, in which case it is suddenly the loudest instrument ever invented. But as the flow changes, the pattern of drops can become less regular. A long gap, then a short gap, then another short gap, then a longer one. The tap is not making random choices. Water gathers, stretches, breaks away, and leaves the surface shaped for the next drop. Each drop changes the conditions for the next one. With the right flow, the rhythm can become chaotic. A household annoyance becomes a small lesson in nonlinear dynamics. Nonlinear is one of those words that sounds more forbidding than it needs to. A linear system is one where changes behave in a nicely proportional way. Push twice as hard and you get twice the response. Add a little more and the result adds a little more. Linear systems are polite. They keep their voices at a reasonable volume. Nonlinear systems are less polite. In them, a small change can produce a big response, or a big change can produce a surprisingly small response. Effects can feed back into causes. Parts can interact in ways that are not simply added together. This is where simple rules begin to generate wild worlds. Many natural systems are non-linear. The atmosphere is non-linear. The heart is non-linear. Ecosystems are non-linear. Fire, fluids, markets, brains and crowds all contain non-linear relationships. This is why they can surprise us. Their parts do not merely stack like bricks. They interact like conversations, and conversations can change direction because of one sentence. Feedback makes non-linearity especially powerful. Suppose a small change makes a system respond in a way that increases that change. That is positive feedback. It can amplify. A small warming can melt some ice. Less ice reflects less sunlight. More sunlight is absorbed. Warming increases. That is a feedback loop. In other cases, feedback stabilizes. A thermostat senses that a room is too cold and turns on heat. When the room warms, the heat turns off. That is negative feedback, and it helps maintain balance. Life depends on both kinds. Too much amplification can run away. Too much damping can become rigid. The living world often finds itself adjusting between them. Simple rules become powerful because they do not act once. They act repeatedly. Repetition lets small effects accumulate. Feedback lets results become causes. Non-linearity lets small changes become large ones. Sensitivity lets nearly identical beginnings separate over time. Put these together, and the world becomes capable of astonishing richness. This is why computer simulations became so important in the study of chaos and complexity. A computer can apply a simple rule many times and show the pattern that emerges. Before computers, it was difficult to see what repeated rules might do over thousands or millions of steps. The human mind is good at many things, but it is not especially fond of doing the same calculation endlessly without complaining. Computers, by contrast, are very patient, provided no one spills tea into them. With computers, scientists and mathematicians began to explore artificial worlds made from simple rules. One famous kind of artificial world is a cellular automaton. The idea is simple. Imagine a grid of little squares. Each square can be in one of a few states, such as alive or not alive, on or off, filled or empty. The state of each square changes depending on the states of nearby squares. That is all. A grid, a few states, a local rule, and repetition. From such plain ingredients, patterns can appear that move, grow, collide, reproduce, vanish, or organize themselves into surprisingly lively forms. Some patterns are stable, some blink back and forth, some travel across the grid like tiny creatures. It can feel oddly alive, even though there is no intention anywhere inside it. The system is only following rules, yet watching it, one begins to understand how complexity might arise without a central commander. This is a profound shift. We often assume order must be imposed from above. A city has planners, a machine has designers, a song has a composer. But many natural patterns are not ordered by a single director. They emerge from local interactions. Ant colonies, for example, can produce organised behaviour without one ant understanding the whole plan. Each ant follows simple signals and responses. Together the colony finds food, builds structures, defends itself and adapts. No ant carries a map of the entire system. The intelligence is distributed. The pattern belongs to the interaction. Bird flocks offer another graceful example. A flock turns as if it were one creature, flowing through the sky in smooth waves. Yet each bird is responding mainly to nearby birds, keeping distance, matching direction, avoiding collisions. No single bird is standing at the front with a clipboard shouting, "Left now, dramatic swirl, everyone look elegant." The global pattern emerges from local rules. Each bird follows simple tendencies, and the flock becomes something more than the sum of individual choices. Fish schools, insect swarms, and even crowds of people can show similar behaviour. Local rules create collective motion. Step too close, move away. See others turning, turn with them. Find an opening, move through it. The pattern that emerges may be fluid, beautiful, and sometimes unpredictable. Complexity does not always require a central plan. Sometimes it grows from many small parts following simple rules near their neighbours. This idea is sometimes called emergence. Emergence happens when a system has properties that are not obvious from the individual parts alone. A single water molecule is not wet in the everyday sense. Wetness emerges when many water molecules interact. A single neuron does not have a thought. Thought emerges from enormous networks of neurons interacting. A single ant does not behave like a colony. The colony emerges from many ants and their signals. Emergence is the science of how together can become something new. Chaos theory overlaps with emergence because both show that the path from simple parts to complex behaviour is not always obvious. A simple rule can generate a pattern. Many simple interactions can create an organised system. A deterministic process can become unpredictable. The world gains depth not by abandoning rules, but by repeating them in connected settings. There is a bedtime gentleness in this if we let it settle. The complexity of your own body, for instance, is not managed by a tiny person sitting inside your head with a master control panel. Your body works through countless local processes. Cells respond to chemical signals, hormones rise and fall, nerves fire, muscles adjust, the heart changes its rhythm, the lungs respond to carbon dioxide and oxygen, temperature is regulated, digestion moves, sleep arrives through shifting patterns in the brain. No single part is doing everything. The whole is coordinated through many interacting rules, and these rules are not stiff like a clock. They are responsive, they adjust, they allow variation. A perfectly rigid living system would not survive very well. Life needs the ability to respond to change. It must be stable enough to hold together and flexible enough to adapt. That balance between order and change is one of the places where the language of chaos becomes useful. Too much order can become brittleness. Too much chaos can become breakdown. Healthy systems often live near the edge, where patterns are stable but not frozen. The phrase edge of chaos is sometimes used to describe systems balanced between rigid order and complete disorder. It is a tempting phrase, partly because it sounds like the title of a very dramatic album. But the idea behind it is serious. Some systems seem most adaptable when they are neither locked into one pattern nor scattered into randomness. They can hold structure while exploring possibilities. They can respond to the environment without losing themselves. In biology, computation and complex systems, this balance has become a powerful theme. Consider the brain. If brain activity were too regular, too locked into one repetitive rhythm, it would lose flexibility. If it were completely random, thoughts and perceptions could not hold together. Instead, the brain seems to operate through structured activity that is always changing, always adjusting, always linking one state to another. Consciousness itself may depend on a balance between stability and variation. You're not a clock, and thankfully not a bowl of static either. You're a living pattern that keeps renewing itself. This is one reason simple rules are so important. They show how a system can be understandable at one level and surprising at another. The basic rule may be easy to state, but the repeated unfolding may produce patterns too rich to compress into a simple prediction. You can know how the pieces interact, but still need to watch the process unfold to see what appears. This is sometimes called computational irreducibility. It means there may be no shortcut to knowing what a system will do except letting it run. The future is not hidden because it is mystical. It is hidden because the process itself is the only way to produce it. This idea feels strange because we like shortcuts, a formula, a forecast, a summary, a neat answer. But some systems resist being summarized in advance. Their behavior is generated step by step. To know the path, you must follow the path. A growing plant, a forming storm, a developing conversation, a life. Some things cannot be fully known from the starting line. At the same time, simple rules do not mean simple meanings. A rule can be mechanical, while the pattern it produces can be beautiful. A snowflake does not need artistic intention to be beautiful. A coastline does not need a designer to be intricate. A flock does not need choreography to move like a dance. Beauty can emerge from process. That may be one of the quiet gifts of this subject. It lets us see natural beauty not as something separate from science, but as something science can deepen. Think again of a fern. Its fronds divide into smaller fronds which resemble the larger form. The plant grows according to biological rules, but the result has a repeating elegance, or think of lightning branching through the sky. It follows paths shaped by electrical conditions, air, moisture, and resistance. The branching looks wild, but not meaningless. Or think of blood vessels spreading through the body, roots searching through soil, cracks forming in dry mud, frost growing on glass. Each pattern comes from local rules and physical constraints. Each one carries the signature of repeated interaction. This is why chaos theory often leads naturally into fractals. Fractals are patterns that show similar structure at different scales. They are not all chaotic, and not every chaotic system creates a fractal you can point to, but they share a family resemblance. They reveal how simple processes can generate complexity that repeats, folds, and branches. A fractal is like nature saying, "I liked that shape, so I made smaller echoes of it, then smaller echoes again." It is not poetry when the mathematics does it, but it certainly feels close. Before we reach those hidden shapes, though, it helps to appreciate the main lesson of simple rules. They free us from the idea that complexity must always be built piece by piece from a complicated plan. Sometimes complexity is grown, sometimes it is iterated, sometimes it emerges when simple parts interact repeatedly. The world does not have to choose between order and surprise. It can have both, because rules can be fertile. They can produce more than they appear to contain. A seed contains instructions for growth, but it does not contain a miniature tree folded perfectly inside it. The tree becomes itself through interaction with soil, water, light, wind, time, and chance. A rule does not have to specify every leaf. It can guide a process that makes leaves possible. That is a different kind of order, less like a blueprint and more like a recipe that changes slightly depending on the kitchen. And as anyone who has tried to bake while tired knows, conditions matter. In the same way, simple physical laws do not need to list every cloud shape, every wave curl, every flame flicker, every branch of every river. They provide the conditions under which such things can unfold. The richness is in the unfolding. The world is not merely a set of objects, it is a set of processes, and processes have histories. They remember where they have been through the state they are in now. That memory can be seen in small ways. The next drop from a tap depends on the shape left by the previous drop. The next bend of a river depends on erosion already done. The next movement of a crowd depends on where people have already shifted. The next thought in your mind depends on the thought before it, and the mood behind it, and the day behind that. Systems carry their past forward, not always as clear memory, but as structure. When simple rules act on structures shaped by previous rules, worlds become wild. This wildness should not be confused with disorder in the ordinary sense. It is not simply mess. It is pattern too complex to be guessed at a glance. It is the difference between a pile of broken sticks and a branching tree. Both may be irregular, but the tree has growth logic. Chaos theory trains the eye to ask whether irregularity may have structure. It asks whether what looks messy may be the visible trace of rules working through time. That is why the subject can feel calming rather than alarming. It does not say the world is out of control in a meaningless way. It says control was never the whole story. The universe is creative with rules. It produces spirals, storms, branches, rhythms, and sudden shifts. It makes patterns that can be studied without being fully pinned down. It is lawful, but not dull, sensitive, but not senseless. And perhaps this gives us a gentler way to think about our own days. A life is not built from grand decisions alone. It is also shaped by repeated small rules. The habit of waking at a certain time, the way you respond to stress, the people you call back, the walks you take, the books you open, the rest you allow. Tiny repeated actions can grow into a pattern. Not instantly, not dramatically, and not with perfect predictability. But over time, repetition matters. Feedback matters. Conditions matter. The wild world of a life is not always created by one dramatic turn. Sometimes it grows from simple rules quietly repeated. Chaos theory does not make that sentimental. It makes it more grounded. Systems evolve through small steps. Small steps interact. Interactions accumulate. Accumulations change the landscape for the next step. That is how rivers carve valleys. That is how habits shape minds. That is how weather systems form. That is how simple rules become wild worlds. So when we look at a curling cloud, a branching tree, a flock of birds, or the shifting pattern of water in a stream, we are not merely looking at pretty complexity. We are looking at the power of repetition. We are looking at local rules becoming global form. We are looking at the universe doing something it does everywhere, turning simple tendencies into layered patterns. And once you begin to see this, the next question quietly appears. If simple rules can create wild worlds, do those wild worlds have hidden shapes? When a chaotic system moves unpredictably, is it wandering anywhere at all, or does it follow an invisible form beneath the motion? The answer leads into one of the most beautiful ideas in chaos theory, the strange attractor, where disorder begins to draw shapes in the dark. At first, the phrase strange attractor sounds as if it belongs in a dusty science fiction paperback, somewhere between a mysterious glowing crystal and a planet that politely refuses to obey gravity. It is a wonderfully odd term. Strange, because the patterns it describes are not the tidy shapes we expect from simple motion. Attractor, because even chaotic motion is often drawn toward a certain kind of behavior, as if the system is wandering freely, but not anywhere it likes. It may be unpredictable in detail, but it is not completely lost. This is one of the great surprises of chaos theory. Chaotic systems can be unpredictable, but they are not always shapeless. They can move in ways that never exactly repeat, and yet those movements may still stay within hidden boundaries. The system does not fly off into every possible future. It returns, circles, folds, escapes, comes close, turns away, and keeps moving through a kind of invisible landscape. If you could see that landscape, if you could turn motion into a shape, you might find that chaos has an architecture. That is what strange attractors reveal. They show us that beneath motion which appears irregular, there may be a hidden form. To understand the idea gently, let us begin with something simpler than chaos. Imagine a marble placed inside a smooth bowl. If you drop it near the rim, It rolls down, climbs up the other side, rolls back, and gradually loses energy. After a while, it settles at the bottom. The bottom of the bowl is an attractor. It is the state the system moves toward. No matter where you start the marble inside the bowl, as long as it stays in the bowl, it eventually ends up at the same resting place. The motion may differ at first, but the destination is stable. This kind of attractor is easy to picture. It is a point. The system ends up still. Many systems have this quality. A hot cup of tea cools toward room temperature. A disturbed pendulum eventually comes to rest. A small ripple on a pond fades. These systems are drawn toward calm. They have attractors that feel familiar, like a soft landing after movement. Now imagine a different system, one that does not settle into a point but repeats a cycle. A clock pendulum, kept moving by its mechanism, swings back and forth again and again. A planet moves around the sun in a regular orbit. Your breathing, while relaxed, rises and falls in a repeating rhythm. These are not point attractors, because the system does not stop. Instead, it moves along a loop. The attractor is the repeating cycle itself. Start the system a little differently, and after a while it may return to the same rhythm. The motion is drawn toward repetition. So far this is still gentle and orderly, a point, a loop, a rhythm. Science is comfortable here. The mind can picture it. Even a sleepy mind can say, "Yes, I understand this one. Please continue quietly." But chaos theory asks us to imagine a third kind of attractor. Not a point, not a simple loop, not a regular rhythm. Instead, a shape made of motion that never closes into perfect repetition, yet never wanders randomly through every possibility. The system keeps returning to the same region, but never in exactly the same way. It traces paths that come close to earlier paths without landing on them. It folds over itself again and again, like dough being stretched and turned, or like smoke curling in a room where the air remembers every tiny disturbance. That is a strange attractor. It is strange because it combines order and unpredictability. It attracts the motion, but it does not force the motion into exact repetition. It gives the system a home, but not a script. The path remains sensitive to tiny differences, so you cannot predict exactly where the system will be far in the future. Yet if you watch long enough, the overall pattern is not meaningless. The motion keeps drawing a shape. This is why strange attractors are so important. They show that chaos is not simply a failure of prediction. It is a form of behavior with its own structure. A chaotic system may be impossible to forecast in detail, but it may still have a recognizable pattern of possibilities. It may still have a hidden shape. The most famous example is often associated with Edward Lorenz and his simplified weather model. When Lorenz studied the results of his equations, the system did not settle down into one state. It did not repeat in a clean circle. Instead, it moved through a pattern that looked like two wings or two swirling loops, folding around one side, then the other, again and again, but never quite repeating. The shape became known as the Lorenz attractor. Its outline has often been compared to a butterfly, which is fitting given the famous butterfly effect. But this butterfly is not fluttering prettily in a garden. It is a map of chaotic motion, a portrait of a system that is both rule-bound and unpredictable. The Lorenz attractor is not a physical object floating somewhere in the atmosphere. You will not see it drifting past your window, unless it has taken a very unusual career path. It is a shape made by plotting the state of a system in an abstract space. That sounds more technical than it needs to. Think of it like this. To describe a moving system, we need to know more than just where it is. We may need to know how fast it is moving, what direction it is going, what its temperature is, how pressure is changing, or some other set of details. If we take those details and imagine them as coordinates in a kind of invisible map, then every moment of the system becomes one point on that map. As the system changes, the point moves. Over time, it draws a path. This invisible map is sometimes called phase space. The name may sound formal, but the idea is simply a space of possibilities. Instead of mapping where something is in ordinary space, it maps the condition of the system. Every possible state has a place. The system moves through this possibility space as it evolves. For a simple pendulum that comes to rest, the path in this space spirals towards stillness. For a repeating system, the path may settle into a loop. For a chaotic system, the path may form a strange attractor, a shape that is never retraced exactly, and yet remains confined within a recognizable region. There is something quietly beautiful about this. Motion becomes drawing, change becomes geometry. A system that appears messy in time can reveal a shape when seen from the right angle. This is true in many parts of science. Sometimes the pattern is not obvious in the thing itself. You need another way of looking. A piece of music, for example, is not just one note after another. It has themes, returns, variations, and structures that may only become clear when you hear the whole. A life is not just a list of days. It has habits, cycles, turning points, returns, and changes that only appear when you step back. In a similar way, a chaotic system may look irregular moment by moment, but when its motion is traced in the right space, a hidden shape begins to appear. A strange attractor is like a memory of where the system tends to go. Not a memory in the human sense, but a structure of tendency. The system may be pulled into certain regions again and again. It may avoid others. It may loop around familiar zones without repeating its path. It has behavior that is constrained, even if it is unpredictable. Imagine a moth flying around a lamp in a dark room. The path may be erratic. It darts, circles, veers away, returns, rises, drops. If you tried to predict exactly where it would be 10 seconds from now, you might fail, and the moth would not apologize. But the moth is not anywhere in the room at random. It is mostly near the lamp. Its motion has a region. The lamp acts like an attractor, though the moth's exact path remains difficult to predict. This is not a perfect scientific example, but it gives the feeling. The system wanders, but within a pull. Strange attractors are more subtle. There may be no physical lamp. The pull comes from the rules of the system itself. The motion is drawn into a certain pattern because of how the system changes from moment to moment. The attractor is not a force in the usual sense. It is a shape created by the system's own dynamics. This idea can help us understand why chaos is not randomness. A random process, in the pure sense, has no deterministic path to trace. It does not follow one exact rule from one state to the next, but a chaotic system does. If you could know its state perfectly, it would unfold according to its rules. The trouble is that tiny uncertainties grow. Still, because it follows rules, it may form an attractor. Randomness scatters. Chaos folds. That word folds is useful. Is. Many strange attractors have a structure that comes from stretching and folding. Imagine a lump of dough. You stretch it out, fold it back, stretch it again, fold it again. Points that were close together can be pulled apart. Points that were far apart can be brought near. The material becomes layered. A chaotic system can do something like this to its possible states. Small differences get stretched apart, creating sensitivity. Then the motion folds back into a bounded region, keeping the system from escaping entirely. Stretching creates unpredictability. Folding creates structure. Together, they create strange attractors. This stretching and folding is why two nearly identical starting points can separate quickly, yet both remain within the same overall pattern. They may end up in different parts of the attractor, following different paths, but they do not simply fly into unrelated behavior. The attractor holds the family of possible motions. You can see an echo of this in stirring liquid. If you place a drop of dye into a glass of water and stir gently, the dye stretches into ribbons. The ribbons fold around, stretch again, and fold again. Soon the colour spreads through the water in complicated patterns. Two tiny bits of dye that started close together may end far apart, yet the motion is still shaped by the container, the stirring, and the fluid. The die does not teleport to the ceiling or file a complaint with the laws of physics. It explores the possibilities allowed by the system. In chaotic motion, a strange attractor is the allowed region of exploration. It is the container of the wildness. One of the reasons this idea mattered so much is that it gave scientists a way to study systems that seemed irregular without treating them as meaningless. A heartbeat, for instance, is not perfectly regular. If it were too perfectly regular, that could actually be a problem. A healthy heart shows variation, subtle changes from beat to beat as the body responds to breathing, movement, emotion, and internal signals. Too much disorder can be dangerous, but too much rigid order can also be unhealthy. The heart lives in dynamic balance. Researchers have used tools related to chaos and attractors to study patterns in heart rhythms, looking for signs of stability, flexibility, and risk. The same style of thinking has touched neuroscience. Brain activity is complex, constantly changing, and deeply sensitive to internal and external conditions. It is not simply random noise, and it is not a clock ticking through fixed states. Patterns of brain activity may move through regions of possibility, returning to certain states, shifting away from others, and forming dynamic structures. Conscious experience itself depends on motion through these patterns. You are not one fixed state. You are a changing system that remains recognizably you. Ecosystems also have attractor-like behavior. A lake, a forest, or a grassland may remain in one stable pattern for a long time, even while individual details change. Then, under pressure, it may shift suddenly into another pattern. A clear lake can become murky. A forest can become grassland. A population can cycle or collapse. These shifts may be hard to reverse because the system has moved toward a different attractor, a different region of stability. This is one reason environmental systems require care. They may absorb disturbance for a while, then change abruptly once thresholds are crossed. Nature is resilient, but resilience is not infinite. Even the planets, those great symbols of celestial order, can become part of this story. A single planet orbiting a star is beautifully predictable. Add more bodies, all pulling on each other, and the motion becomes more complicated. The solar system is stable over human timescales, thankfully, because none of us wants Jupiter to start improvising. But over extremely long stretches, gravitational interactions can show chaotic features. Tiny differences in position can grow. Orbits remain bounded, yet exact prediction becomes limited. The heavens, once imagined as perfect clockwork, have their own delicate sensitivities. The presence of strange attractors changes the way we think about prediction. If a system has a strange attractor, we may not know exactly where it will be in the distant future, but we can learn about the shape of its possible behavior. We can ask what regions it tends to visit. We can ask how often it moves through certain states. We can ask what patterns remain stable and what changes might push it elsewhere. This is a different kind of knowledge, less like reading a timetable and more like understanding the habits of a landscape. Imagine you're watching a cat wander around a house. You may not know exactly where the cat will be at a particular moment. Cats are famously committed to making prediction difficult. But over time, you might learn its attractors: the sunny windowsill, the warm laundry basket, the chair you wanted to sit in, the exact piece of paper you were trying to read. The cat's path is not perfectly predictable, but its behavior has tendencies. It returns to certain places. It has a hidden map of comfort and mischief. Chaotic systems are not cats, though some of them seem equally unwilling to follow instructions. But the idea of tendency is helpful. A strange attractor tells us that a system has a range of preferred behavior. It is not free to do absolutely anything. It is constrained by its rules, its energy, its feedback, and its structure. This is why strange attractors are visually captivating when plotted. They look like delicate loops, folded ribbons, layered wings, or tangled threads. The paths may never cross exactly because crossing would mean the system has returned to the same state and would then repeat from there. Instead, the path comes close, again and again. weaving a shape with endless variation. It is like a dance where the dancer keeps returning to familiar steps but never performs the same sequence twice. There is a lesson in that image. Repetition does not always mean sameness. A system can return without repeating. It can stay within a pattern while constantly changing. It can be recognizable and unpredictable at once. Many things in life have this quality. Sleep comes each night, but no night is exactly the same. Seasons return, but each winter has its own weather. Conversations with an old friend may circle familiar themes, but they still unfold differently. The body breathes again and again, but every breath is slightly altered by the one before it. Strange attractors give science a way to speak about this mixture of recurrence and novelty. They also remind us that hidden shapes may exist where our ordinary senses see only irregularity. A dripping tap may seem merely annoying, but its rhythm can trace patterns. Weather may seem endlessly variable, but its simplified models reveal attractors. A heart rhythm may seem just uneven, but its variation may contain information about health. The shape is not always visible directly. Sometimes it appears only after careful observation, after translating change into a different kind of space. This is one of the quiet powers of science. It does not only discover new things, it discovers new ways to look. A telescope turns faint light into worlds. A microscope turns smallness into landscape. A graph turns change into shape. A model turns motion into understanding. Strange attractors are part of that tradition. They are not objects in the hand, but ways of seeing the hidden geometry of behavior. And the geometry is often surprising. Traditional geometry likes clean lines, circles, triangles, spheres, and smooth surfaces. Strange attractors are not usually smooth in that classical way. They can have roughness, folds, gaps, and intricate structure. Look more closely, and new detail appears. Look closer still, and there may be more. They seem to live between dimensions, not quite like ordinary surfaces, not quite like simple curves. This is where chaos theory begins to touch the world of fractals. A fractal is a pattern with detail that continues across scales. It may show smaller versions of similar structures again and again. Not always exactly, but often with a recognizable echo. Strange attractors can have fractal structure because the stretching and folding process creates layers within layers. The path of motion does not fill space smoothly. It gathers into a complex set with endless fine detail. The attractor is strange partly because its shape is not simple, it has hidden intricacy. This might sound abstract, but nature is full of shapes that prepare us for the idea. A coastline grows more detailed the closer you look. A tree branch divides into smaller branches. A fern repeats its form in smaller leaflets. A cloud has soft edges filled with smaller soft edges. A lightning bolt branches, and the branches branch again. These are not strange attractors in the strict sense, but they help the eye understand how nature can build forms that are neither smooth nor random. They are structured roughness. Strange attractors are structured motion. That phrase may be the simplest way to hold them. They are not merely shapes in space. They are shapes made by change. They reveal the pattern of a system over time. If a mountain is a shape of rock and a river channel is a shape carved by water, then a strange attractor is a shape carved by motion through possibility. And perhaps this is why the idea feels so satisfying. Chaos theory could have left us with only uncertainty. It could have said, tiny differences grow, prediction fails, good luck with your picnic. But strange attractors offer something deeper. They say that unpredictability can have form. They say that even when exact future details are lost, the overall behavior may still be studied. They say that chaos has places it likes to go. This changes the feeling of chaos. Instead of imagining a mess spreading in all directions, we can imagine a restless system moving within a hidden design. Not designed by intention, but shaped by rules. The pattern is not imposed from outside. It emerges from the system itself. This is a very different kind of order from the old clockwork universe, but it is order all the same. The old dream wanted every future point to be knowable. Chaos theory says that may be impossible for many systems, but strange attractors say there is still something to know. We may not know the exact path, but we can learn the shape of the wandering. We may not predict every turn, but we can understand the landscape of turns. We may not remove uncertainty, but we can see its boundaries. There is a gentle comfort in that, especially at night. The mind often wants certainty before rest. It wants every question answered, every tomorrow arranged, every possible outcome lined neatly on a shelf. But many parts of life are more like strange attractors than timetables. They have patterns, habits, loops, and tendencies. They do not repeat exactly. They wander, they return, they change, they remain recognizable. Perhaps calm is not the ability to know every detail in advance. Perhaps it is the ability to recognize the hidden shape of things, even when the path is still moving. The universe, seen through strange attractors, becomes less like a rigid machine and more like a system of dances. Some dances are simple, repeating the same steps. Some slow and settle into stillness. Some never repeat, yet never lose their character. The weather dances. The heart dances. Rivers, flames, crowds, ecosystems, and perhaps even thoughts move through invisible spaces of possibility. Their paths may be sensitive, but not meaningless. And once we accept that motion can draw hidden shapes, it becomes easier to see why the natural world is filled with patterns that repeat, branch, fold, and echo themselves across scale. The strange attractor opens the door to a wider family of forms that look rough but carry order, forms that appear in clouds, coastlines, lungs, trees, rivers, and lightning. To follow that door, we must let geometry become less polished and more alive, because the next part of the story belongs to fractals, the patterns that repeat inside nature. The first time you notice a fractal in nature, it can feel as though the world has been quietly repeating itself behind your back. A fern leaf is not just a leaf. It is a little collection of smaller leaves, and those smaller leaves seem to carry the same idea in miniature. A tree is not just a trunk with branches. It is a trunk that divides. Then those branches divide, then the smaller branches divide again, until the pattern becomes too fine to follow. A river seen from above splits into channels, and those channels split into smaller streams, and those smaller streams reach into the land like veins. Lightning does the same thing across the sky for a fraction of a second, branching and branching again, as if the storm has suddenly drawn a nervous system in light. Fractals are patterns that contain echoes of themselves at different scales. They are shapes where the small part resembles the larger part, not always perfectly, not like a photocopy, but in a family resemblance kind of way. Nature does not usually repeat with the stiff precision of wallpaper. It repeats with variation. It tries an idea again, a little smaller, a little bent, a little changed by wind, water, growth, stone, or chance. That is part of why fractals feel alive. They are structured but not rigid, familiar but not mechanical. They show us a world where order can be rough around the edges. This matters to chaos theory because chaotic systems often create patterns that are not smooth and simple. They fold, stretch, branch, and layer. Their hidden shapes can have fine detail that keeps appearing the closer you look. In the last part of our journey, we wandered through strange attractors, those hidden shapes made by motion in a system that never repeats exactly. Fractals belong nearby. They are not exactly the same thing, but they share a deep connection. Both show that the world can be irregular without being meaningless. Both show that complexity can have structure. Both ask us to stop expecting nature to be made only of circles, straight lines, and neat polished surfaces. Classical geometry is beautiful, but it is also a little too tidy for the natural world. It gives us perfect circles, triangles, cubes, spheres, and straight lines. These are useful, elegant, and deeply important. But if you walk outside and look carefully, nature is rarely so smooth. A mountain is not a cone, A cloud is not a sphere. A coastline is not a clean line. A tree is not a cylinder with little cylinders attached, though somewhere perhaps a very tired textbook illustrator has tried. Natural shapes are rough, broken, branching, folded, wrinkled and layered. They look messy only because our older geometry was not designed to describe them well. Fractal geometry offered a new way of looking. It said that roughness itself can have pattern. Irregularity can have rules. A coastline may twist and turn, but those twists may show similar kinds of detail at different scales. A cloud edge may look soft and ragged, but zoom in and the raggedness continues. A mountain ridge has large peaks and smaller ridges and tiny cracks, all nested inside one another. Fractals are a way of studying the shapes that ordinary geometry politely avoided, perhaps because they had mud on their boots. One of the classic examples is the coastline. Imagine looking at a coast from high above. You see the broad outline, bays, headlands, islands, and long curves. Now move closer. The line becomes more complicated. Small coves appear, rocks break the edge, move closer again, and there are smaller cracks, pools, pebbles, grains of sand, tiny wet boundaries between water and land. The closer you look, the more detail appears. The coastline does not become simpler at smaller scales. It keeps offering more edge. This leads to a strange question. How long is a coastline? At first, that sounds easy. Just measure it. But the answer depends on the length of the measuring tool. Use a long ruler, and it skips over small wiggles. Use a shorter ruler, and it follows more detail, making the measured length longer. Use an even shorter ruler, and the length grows again. The coast is not changing. Your method of measuring is changing. The smaller the scale, the more detail you include. The coastline becomes a lesson in how nature resists simple measurement. This does not mean coastlines have no length in any practical sense. Maps work, ships navigate, people walk along beaches and eventually find ice cream. But it does show that natural edges can have a kind of scale-dependent complexity. Their detail does not vanish when you zoom in. It keeps unfolding. That is a fractal quality. Trees show this more gently. A trunk divides into large branches. Large branches divide into smaller branches. Smaller branches divide into twigs. Twigs hold leaves, and in many leaves the veins also branch. The same basic idea appears across scale, a main channel dividing into smaller channels which divide again. This is not just decorative. Branching is useful. It allows a tree to spread its leaves into sunlight while transporting water and nutrients. It allows roots to explore soil efficiently. The shape is beautiful because it is functional, and functional because it is shaped by simple repeated rules of growth. Your own lungs also carry a branching pattern. Air enters through a main passage, then moves into smaller passages, then smaller ones again, until it reaches tiny spaces where oxygen can pass into the blood. The branching structure allows a large surface for exchange to fit inside the body. If the lungs were built as one simple hollow bag, they would be much less effective. Instead, they branch and branch and branch, creating a hidden forest of airways inside the chest. Every calm breath you take is moving through a biological fractal, though it is usually best not to think about that too vividly while trying to sleep. Blood vessels form another branching network. Large arteries divide into smaller arteries, then into tiny vessels reaching deep into tissues. Veins gather blood back through a mirrored kind of branching. The body needs to deliver materials everywhere, and branching is an efficient way to reach many places from a few main routes. Rivers do the same on the surface of Earth. Roots do it underground. Nerves do it through living tissue. The same pattern appears because the problem appears again and again. How do you connect one source to many destinations? Branch. This is one reason fractals feel so widespread. They are not a decorative accident. They are often the result of growth, transport, flow, and efficiency. Whenever something spreads through space, whether water, air, blood, electricity, roots, cracks, or fire, branching patterns can emerge. The details differ, but the underlying logic echoes. Lightning is one of the most dramatic examples. During a storm, electrical charge builds between clouds and the ground or within clouds themselves. When the conditions become right, a discharge forms, seeking a path through the air. The path branches because the air is uneven, and the electrical conditions vary from place to place. The result is sudden and jagged, a bright tree of energy across the sky. It lasts only a moment, but in that moment the storm draws a fractal line. It is wild, but not meaningless. It follows physical conditions, branching through the easiest available paths. Cracks in dry mud and broken glass also create branching patterns. When stress moves through a material, it does not always spread smoothly. It concentrates, splits, changes direction, and follows weaknesses. A small crack can grow, divide, and create a network. Again, simple local rules create complicated shapes. The material does not plan the crack. It responds to forces. The pattern is the memory of that response. Snowflakes bring another kind of repetition. Their six-sided structure comes from the arrangement of water molecules in ice, and their branching growth depends on temperature and moisture. As the snowflake falls through changing air, different parts of it grow at different rates. Tiny variations create delicate shapes. The result is a form that feels almost too intricate to come from ordinary physical rules. But it does. The snowflake is not carved by a miniature artist. It is grown by conditions. Its complexity is the history of the air it passed through. This is one of the central lessons of fractals. Shape can be history. A tree records growth. A river network records erosion and flow. A snowflake records temperature and moisture. A crack records stress. A lung records biological development. The pattern you see is not merely a shape sitting there. It is the trace of a process. That idea connects back to chaos theory. Chaotic systems are processes, they unfold in time. Their patterns are not imposed once and then finished. They are generated through repeated change. Fractals give us a way to see how repeated processes can leave behind detail at many scales. They make complexity visible. The mathematician Benoit Mandelbrot helped popularize fractal geometry and gave the field its modern name. He was fascinated by roughness, by the shapes of clouds, coastlines, markets, and natural forms that did not fit neatly into traditional geometry. His work helped show that the irregular shapes of the world were not beyond mathematics. They simply needed a different kind of mathematical language. Instead of smoothing nature down until it became easy, fractal geometry tried to meet nature where it actually was, with all its bumps, branches, and folds. One famous fractal associated with Mandelbrot is a shape generated by repeating a very simple procedure. The details of that procedure belong to mathematics, and we do not need to walk through them here. What matters is the result. The image has a dark, central shape surrounded by endless intricate boundaries. Zoom in, and new forms appear. Zoom in again, and more appear. Similar shapes return at smaller scales, surrounded by filaments, bulbs, spirals, and delicate structures. It is astonishing because the rule that creates it is simple, but the pattern seems endlessly rich. It feels like opening a small box and finding a universe inside. That is the magic of repetition. Not magic in the supernatural sense, but magic in the human sense of wonder. A simple process repeated many times can produce detail beyond what we would expect. Fractals make that visible in a way that is hard to forget. Nature, of course, is not usually an exact mathematical fractal. A real fern does not repeat forever. A tree stops branching at twigs. Lungs stop at tiny air sacs. Coastlines eventually reach grains of sand, molecules, atoms. The real world has limits. It has materials, energy, growth constraints, and physical scales where the pattern ends. So when we call a natural pattern fractal, we usually mean it has fractal-like qualities across a range of scales. It repeats enough to matter, enough to help us understand its structure, but not infinitely. This is important because it keeps the idea grounded. Fractals are not a secret claim that everything repeats forever in a perfect mystical pattern. They are a way to describe how many natural forms show similar detail at different scales. The resemblance may be approximate but useful. Nature repeats with roughness, not with copy and paste. There is a quiet beauty in that imperfection. A perfect repeating pattern can become sterile. Nature's fractals are alive with difference. The smaller branch resembles the larger branch, but it has been shaped by its own light, wind, space, and history. The smaller river resembles the larger river, but it has its own stones and slopes. The smaller crack resembles the larger crack, but it follows its own local weakness. Repetition and variation work together. The pattern holds, but the details breathe. This is why fractals appear so often in art and design. They feel natural to the eye. We are used to seeing layered detail in forests, clouds, mountains, waves, flames, and skin. A scene that contains only perfect smooth shapes can feel artificial. A scene with fractal-like texture feels more real. The eye enjoys complexity at different scales. It wants broad forms and small details. It wants something to recognize and something to explore. Forests are full of this layered structure. From far away, a forest is a mass of green. Closer, individual trees appear. Closer still, branches, leaves, veins, bark textures, moss, and tiny patterns in the soil. The forest never becomes one simple thing. It becomes many things nested together. That nesting is part of what makes natural environments calming for many people. The mind can wander through levels of detail without reaching a hard edge. There is always something more to notice, but not necessarily in a stressful way. The pattern is rich, yet familiar. Clouds do something similar. From a window, a cloud may look like one soft shape. Look longer, and its edges curl and break into smaller billows. Those billows have smaller textures, and those textures have smaller variations. The cloud is constantly changing, but it keeps a recognizable roughness. It is neither smooth nor random. It is a floating fractal made of water droplets, air currents, heat, and time. Fire, too, has this quality. A flame flickers upward, splits, curls, vanishes, reforms. The outline is never the same twice, but it has a recognizable behavior. Small tongues of flame resemble larger tongues. Turbulent air stretches and folds the hot gases. The pattern dances at the edge of predictability. It is one reason humans can stare at a fire for so long. The motion is not repetitive enough to be boring, and not random enough to be meaningless. It rests somewhere in between, where the brain can relax into changing order. This in-between quality is central to both fractals and chaos. We're not looking at perfect order. We're not looking at total disorder. We are looking at structured complexity. And structured complexity is everywhere in living systems. A cauliflower can show it at the dinner table. Certain varieties, especially the pointed green kind, often called Romanesco, display spiraling patterns made of smaller versions of the whole form. The vegetable looks like it has been grown by a mathematician with a flair for drama. But again, the pattern comes from growth. Cells divide, tissues expand, and the plant repeats developmental rules in space. The result is edible geometry, which is one of the more practical forms of beauty. The human brain also contains branching structures. Neurons extend long fibers and many branching connections, allowing signals to pass through networks. The surface of the brain folds into ridges and grooves, increasing area within the skull. The details are not simple fractals in the strict mathematical sense, but they show the same broader theme. Biological systems often create complexity by folding, branching, and repeating structure across scales. Even time patterns can have fractal qualities. Some processes show bursts within bursts, quiet periods interrupted by activity, with similar patterns appearing over different durations. Earthquakes, financial markets, heart rhythms, and neural activity have all been studied for scale-based patterns. This does not mean they are easy to predict. In fact, fractal structure often appears in systems where exact prediction is difficult. But it does mean there may be patterns in the irregularity. That phrase is worth holding gently. Patterns in irregularity. It is almost the whole spirit of this journey. Fractals also help explain why measuring nature can be difficult. If a pattern has detail at many scales, then a single measurement may not capture it fully. The length of a coastline depends on scale. The roughness of a surface depends on how closely you look. The branching of a tree can be described at the level of the trunk, the branch, the twig, or the leaf vein. There is no single view that contains everything. Understanding comes from moving between scales. Science often does this. It zooms out and zooms in. A weather system can be studied as a whole storm, but also as cloud formation, air pressure, moisture, and tiny droplets. A body can be studied as organs, tissues, cells, molecules. An ecosystem can be studied as a landscape, species, individuals, genes, nutrients, and flows of energy. Fractals remind us that scale is not just a technical detail. It changes what we see. This is one reason the natural world can feel endless. Not endless in the literal sense, but rich enough that attention can keep finding new levels. A leaf is simple until you look closer. A stone is simple until you notice its grains, cracks, colours, and history. A wave is simple until you see ripples on its surface and foam at its edge. The world becomes deeper through scale. Chaos theory and fractals changed science partly because they made this depth respectable. They gave scientists tools to study roughness, irregularity, and complex pattern without dismissing them as noise. They said, perhaps the noise has structure. Perhaps the rough edge is the important part. Perhaps the irregular rhythm tells us something. Perhaps what looks messy is not a failure of order, but another kind of order. This is a generous way to look at nature. It does not force everything into perfect smoothness. It allows the world to be jagged, branching, and unfinished. It makes room for the shapes we actually see. And it also gives us a different emotional feeling about complexity. When life feels tangled, we may think of tangles as evidence that something has gone wrong. But in nature, tangling is often how things grow. Roots tangle through soil to find water. Blood vessels branch through tissue to keep cells alive. Rivers carve complicated paths because landscapes are varied. The brain forms dense networks because thought and memory require connection. Complexity is not automatically disorder. Sometimes it is adaptation. Sometimes it is resilience. Sometimes it is the shape of life doing what it must do. Of course, not every tangle is healthy. A system can become too chaotic, too unstable, too stressed. Forest fires can spread destructively. Blood vessels can grow in harmful ways. Weather systems can become dangerous. Chaos and fractal pattern are not always gentle, but understanding their structure gives us a way to study them more clearly. It helps us see how patterns form, how they spread, where they may break, and how small changes at one scale can influence larger scales. That last point brings us back to the butterfly effect. Fractals often connect scales. A small branch resembles a larger branch. A small stream contributes to a river. A tiny crack becomes part of a larger fracture. A local air current feeds into a larger weather pattern. In systems with fractal structure, small and large are not entirely separate. They speak to each other through the shape of the system. This does not mean every small thing controls the large thing, but it does mean that nature often builds pathways between scales. The tiny and the vast are connected by repeated patterns, branching networks, and feedback. A lung connects the breath at the mouth to tiny exchanges deep inside the body. A river network connects raindrops on hillsides to broad currents at the sea. A tree connects sunlight gathered by leaves to water drawn from roots. Scale is a ladder and fractal patterns are often the rungs. As we settle with this, the world may begin to look different. The veins in a leaf are not just veins, they are part of a repeating strategy of distribution. The shape of a cloud is not just fluff, it is turbulence made visible. A coastline is not simply the edge of land, it is a record of waves, rock, time and scale. A heartbeat is not just a beat, it is part of a changing rhythm inside a living network. The deeper lesson is not that everything is secretly the same. A fern is not a storm, a lung is not a river, lightning is not a root, but they share patterns because they share problems of growth, flow, branching and change. Nature reuses useful forms, not with perfect copying, but with variations suited to each situation. Fractals are one way we notice that reuse, and perhaps that is why they feel so satisfying. They show unity without sameness. They let us see connections without flattening the world into one simple idea. The universe is not repeating itself because it lacks imagination. It is repeating certain strategies because those strategies work. Branching reaches, folding fits, roughness absorbs, layering creates surface, repetition builds richness. In the quiet of a science for sleep journey, fractals offer a particularly soft kind of wonder. They do not require us to imagine distant galaxies or strange particles, though those are wonderful too. They are right here, in houseplants, in clouds outside the window, in frost on glass, in your lungs as you breathe, in the branching vessels that keep you warm and alive. The pattern that shapes a river basin also has echoes inside the body resting under a blanket. The universe does not place its mysteries only far away. Sometimes it grows them in leaves, so fractals become a bridge. They connect the visible world to chaos theory. They show how simple repeated processes can create complex forms. They show how roughness can have order. They show how patterns can stretch across scales. And they prepare us for the next step, because if fractal branching lives in trees, rivers, lungs and blood vessels, then chaos itself does not belong only to weather and mathematics. It lives in biology. It appears in rhythms. It moves through the beating heart, the firing brain, the shifting body, and the countless living systems that must stay balanced while always changing. It is tempting to imagine the human body as a machine that wants perfect regularity, a steady heart, a steady breath, a steady brain, a steady temperature, everything ticking along like a well-polished clock in a quiet hallway. There is comfort in that image because clocks feel dependable. They do not usually have moods. They do not suddenly decide that 3 p.m. is an excellent time to crave toast. They simply tick and tick and tick. But the body is not a clock. It is alive. And living things are not held together by perfect repetition. They are held together by constant adjustment. This is where chaos theory begins to feel very close to home. We have followed chaos through weather, simple rules, strange attractors, and fractal patterns in nature. We have seen how systems can follow rules and still behave in ways that are hard to predict. Now the same idea moves inward, beneath the skin, into the rhythms that keep us alive. The body is full of patterns that are ordered without being rigid, variable without being random, and sensitive without falling apart. A healthy living system is often not one that stays perfectly still. It is one that can respond. Your heart is a good place to begin because it is so familiar and so easily misunderstood. We often describe a healthy heartbeat as regular, and in one sense that is true. The heart should not be beating in a completely chaotic or uncontrolled way. It needs coordination. It needs electrical signals to travel properly. It needs muscle cells to contract in sequence. If that order breaks down too far, the result can be dangerous. But a healthy heartbeat is not perfectly regular like a metronome. In fact, the time between beats changes slightly from one beat to the next. This variation is normal. More than normal, it is often a sign that the heart is responding well to the body. When you breathe in, your heart may speed up a little. When you breathe out, it may slow down slightly. When you stand, walk, worry, rest, digest, sleep, or hear an unexpected noise from somewhere in the house, and briefly wonder whether it was the fridge or a small ghost with poor manners, your heart adjusts. It listens to the needs of the body and responds. This subtle beat-to-beat variation is called heart rate variability. It is not chaos in the ordinary sense of confusion. It is controlled flexibility. A heart with healthy variability can adapt to changes. It can shift with breathing, movement, stress, relaxation, and internal signals from the nervous system. If the rhythm becomes too irregular, that can be a problem. But if it becomes too rigid, that can also be a warning. Life often lives between the extremes. That idea is worth letting settle. Too much disorder is dangerous. Too much order can be dangerous too. A perfectly mechanical heart rhythm might sound ideal at first, but the body does not live in a perfectly mechanical world. It lives in a world where you stand up, sit down, climb stairs, eat, dream, panic mildly over unread emails, calm down, fall asleep, wake up, and try to remember why you walked into the kitchen. Each of these moments changes the body's needs. The heart must not simply keep time, it must keep up. The heart is guided by electrical activity, hormones, blood pressure changes, oxygen demand, and signals from the autonomic nervous system. That nervous system includes branches often described as speeding things up and slowing things down. One prepares the body for action, the other supports rest, digestion, and recovery. A healthy rhythm emerges from the ongoing conversation between them. It is not one signal barking orders forever. It is a living balance. Chaos theory helps researchers think about this balance, because heart rhythms can show complex patterns over time. The pattern is not random noise, and it is not a simple repeating clock. It has structure across many timescales. There are fast variations with breathing, slower variations with movement and posture, and longer changes with sleep, stress, illness, or recovery. The heart is part of a system that is always adjusting, and those adjustments leave patterns. When doctors look at the heart, they often need to distinguish useful variability from dangerous instability. Some rhythms are healthy and flexible, others are abnormal and risky. For example, in some serious arrhythmias, the electrical activity of the heart becomes disorganized. The pumping action can fail because the timing between cells is broken down. In other cases, the rhythm may become too locked into an unhealthy pattern. The challenge is not simply to ask whether the heart is regular or irregular. The deeper question is what kind of irregularity is present. That is a very chaos theory kind of question. Not all irregularity is the same. A crack in a wall, a river network, a heartbeat, and static on an old radio may all look irregular in different ways, but their causes and meanings are not the same. Chaos theory teaches the eye and the mind to ask whether there is hidden structure, whether the variation has a pattern, whether the system is adapting or failing to adapt. The brain gives us an even richer example. The brain is often described as the most complex system we know, and for once that phrase is not just a compliment brains gave themselves. It contains vast numbers of nerve cells, each connected to many others, sending electrical and chemical signals in constantly changing patterns. These signals do not simply flow in one direction like water through a pipe. They loop, feedback, amplify, quiet down, synchronize, desynchronize, and shift depending on attention, memory, emotion, sleep, hunger, and the outside world. If the heart is a rhythm section, the brain is a whole orchestra that is also writing the music, listening to it, changing instruments, and occasionally interrupting itself to remember an embarrassing thing from 10 years ago. It is not a simple machine. It is a dynamic system. Brain activity has patterns. During deep sleep, certain slow rhythms become more prominent. During alert attention, other patterns appear. During dreaming, the brain becomes active in ways that are partly similar to waking and partly very different. When we concentrate, networks coordinate. When we relax, other networks become more active. When we remember, imagine, plan, or worry, the brain moves through changing states. These states are not fixed rooms. They are more like regions of activity that the brain can enter, leave, and revisit. That sounds very much like the language of attractors. In neuroscience, some researchers use attractor ideas to think about how the brain settles into patterns of activity. A memory, for instance, may be thought of as a stable pattern that the brain can return to. A perception may arise when brain activity settles into a certain interpretation of incoming signals. A mood may involve the brain and body repeatedly returning to certain patterns. These are not simple one-to-one explanations, and we should be careful not to make the brain sound easier than it is. The brain does not become simple just because we give it a tidy metaphor. But attractor thinking offers a useful way to describe how patterns can be stable without being frozen. You might notice this in ordinary experience. A thought can pull other thoughts toward it. You remember one place, and suddenly a person connected to that place appears in memory, then a song, then a smell, then an entire scene. The mind does not move randomly, it follows connections. Some thoughts are like small valleys. Once you enter them, related memories and feelings gather nearby. This is not the same as a mathematical attractor in a strict sense, but it gives the feeling of how a system can be drawn into patterns. The brain also shows why too much order can be a problem. A healthy brain needs coordination, but it also needs flexibility. If activity becomes too synchronized in the wrong way, it can produce seizures. In a seizure, large groups of neurons may fire together in abnormal patterns. This is not healthy order. It is excessive synchronization, a kind of rigid storm inside the nervous system. On the other hand, if brain activity becomes too disorganized, useful thought and perception cannot hold together. So again, life sits between extremes. The brain must be organized enough to function and flexible enough to adapt. This balance is one reason sleep is so important. Sleep is not simply the brain turning off. If only it were that simple. Sleep is active, structured, and changing. The brain moves through stages, shifting rhythms across the night. The body repairs tissues, regulates hormones, supports immune function, and processes memory. Sleep helps reset and reorganize the systems that keep waking life stable. It is not empty time, it is maintenance time, though with better dreams and fewer invoices. During sleep, the brain and body move through cycles. Breathing changes, heart rate changes, temperature changes, hormones rise and fall. The sleeping body is not perfectly still internally, it is quietly adjusting. A sleeping person may look calm from the outside, but inside there is a carefully managed set of rhythms, loops, and transitions. The body is doing what living systems do. It is maintaining order by changing. That phrase may sound contradictory at first, but it is central to biology. The body maintains stability through constant change. This is often called homeostasis. Your temperature, blood sugar, blood pressure, oxygen levels, and many other internal conditions must stay within certain ranges. But they do not stay there by doing nothing. They stay there through feedback loops. If you get too warm, you sweat and blood vessels near the skin may widen. If you get too cold, you shiver and blood vessels may narrow. If blood sugar rises, hormones help move it into storage or use. If carbon dioxide builds up, breathing changes. The body is a whole network of correction systems. A thermostat is the simple household version of this idea. The room gets too cold, heating turns on. The room warms, heating turns off, but the body is far more complex than a thermostat. Many systems overlap. Signals can reinforce or oppose one another. The same hormone may affect several organs. The same organ may respond differently depending on time of day, stress, food, illness, or sleep. Feedback in biology is layered, and layered feedback can produce complex behavior. This is where chaos theory becomes more than a metaphor. Living systems are full of non-linear relationships. A small change in one signal may produce a large effect in one context and a small effect in another. A system may respond differently depending on its history. Timing matters, feedback matters, sensitivity matters. The body is not a simple set of switches, it is a dynamic network. Take breathing. Most of the time, you do not think about it. Breath rises and falls quietly, adjusted by the brainstem and influenced by carbon dioxide, oxygen, emotion, posture, speech, movement, and attention. If you run, breathing changes. If you sleep, breathing changes. If you become anxious, breathing may become shallow or rapid. If you deliberately slow your breathing, it can affect heart rhythm and calm the nervous system. Breath is both automatic and partly voluntary, which is a rather strange arrangement when you think about it. The body trusted us with a manual control for something vital, and most of the time we wisely forget to interfere. Breathing and heart rhythm are linked. As breath changes, heart rate changes. As emotional state changes, both may change together. This coupling is one example of how biological rhythms interact. The body is not made of separate clocks ticking independently. It is more like a network of rhythms that influence one another. Some rhythms are fast, like heartbeats and breaths. Some are slower, like sleep cycles. Some are daily, like circadian rhythms. Some are monthly or seasonal. Life is layered time. The immune system also behaves as a complex dynamic system. It must respond to threats without attacking everything in sight. It must remember past infections, coordinate many kinds of cells, amplify responses when needed, and calm them when the danger is gone. Too weak a response can allow disease to spread. Too strong or misdirected a response can damage the body. Again, health is not maximum activity or minimum activity. It is appropriate activity, timed and regulated. The endocrine system, which uses hormones as chemical messengers, adds another layer. Hormones do not simply turn things on and off. They rise and fall in rhythms. Cortisol, for example, follows a daily pattern related to waking and energy regulation. Melatonin rises in the evening to support sleep. Insulin responds to food and helps regulate blood sugar. Reproductive hormones follow longer cycles. Stress can shift many of these patterns. Light can shift circadian signals. Food timing, sleep, exercise and illness can all feed into the network. The body is full of loops within loops. Because of all this, living systems often show variability that is meaningful. A healthy system does not hold one exact value forever. It fluctuates within a range. Temperature varies, heart rate varies, hormones vary, attention varies, mood varies. The point is not to remove all variation. The point is to maintain flexible stability. This is where the older machine metaphor becomes too limited. A machine is often judged by how consistently it repeats. A living body is judged by how well it adapts. If a car engine changes rhythm unexpectedly, that may be bad news. If your heart changes rhythm slightly with breathing, that is part of being alive. The body is not trying to be a perfect metronome. It is trying to be responsive enough to survive breakfast, stairs, surprises, sleep, and the occasional existential thought at midnight. Chaos in biology does not mean the body is out of control. It means that biological order is dynamic. It includes variation, feedback, and sensitivity. It allows living systems to move through changing conditions without collapsing. A rigid system may look stable, but it may be fragile. A flexible system may look irregular, but it may be robust. This is seen in movement too. When you walk, your steps are not perfectly identical. They vary slightly. The variation helps your body adjust to small changes in the ground, balance, fatigue, and attention. A perfectly identical step every time would not be ideal on an uneven path. Healthy movement contains controlled variability. The nervous system and muscles adjust constantly. You do not calculate every movement consciously. Your body solves the problem as you go. Even standing still is not truly still. If you stand upright, your body sways slightly. Muscles make tiny corrections. Sensors in your inner ear, eyes, joints and skin help keep balance. The body is always falling a little and correcting a little, though usually so smoothly that you do not notice. Balance is not the absence of movement. It is the management of movement. This is another quiet lesson from living chaos. Stability is often active. A tree stands because it grows roots, flexes in wind, transports water, repairs damage, and changes with seasons. A person stands because the nervous system, muscles, senses, and skeleton make constant adjustments. A mind stays coherent because brain networks keep coordinating and revising. The stillness we see is supported by motion we do not see. The body also has thresholds, and thresholds are important in chaotic and complex systems. A small change may have little effect for a while, then a system may shift suddenly once a limit is crossed. In biology, this can appear in many ways. A neuron may receive signals without firing until enough input arrives and it sends a pulse. A fever may begin when immune signals push temperature regulation into a different state. Fatigue may build gradually, then suddenly feel overwhelming. Emotional stress may be manageable for a long time, then a small extra demand can feel like the final straw. Systems can absorb change until they cannot. This does not mean bodies are unreliable. It means they are complex. They have reserves, buffers, feedback loops, and tipping points. Understanding health often means understanding not only individual parts, but how the parts interact over time. A heart is not just a pump. A brain is not just a collection of neurons. Sleep is not just unconsciousness. Stress is not just a feeling. Each is part of a network. Modern medicine often needs both approaches. It needs detailed knowledge of parts, cells, molecules, organs, and mechanisms. But it also needs system thinking, because symptoms often emerge from interactions. Blood pressure involves the heart, vessels, kidneys, hormones, nervous system, salt balance, stress, activity, and more. Mood involves brain chemistry, sleep, social life, memories, hormones, inflammation, habits, and environment. Digestion involves nerves, microbes, immune signals, movement, food timing, and emotion. The body is not a filing cabinet with each issue in a separate drawer. It is more like a very busy garden where roots overlap underground. That garden image is useful because gardens require balance rather than absolute control. Too much water can harm. Too little water can harm. Sunlight matters. Soil matters. Timing matters. One plant affects another. A garden is organized but alive. It changes. It needs attention, not command. The body is similar. It is self-organizing, responsive, and full of feedback. Self-organization is another important idea connected to chaos and complexity. It means that order can arise from the interactions of many parts without a central controller specifying every detail. The heartbeat emerges from electrical and cellular processes coordinated through the heart. Brain patterns emerge from networks of neurons. Immune responses emerge from many cells signaling and responding. The body has control systems, certainly, but many patterns are distributed. No tiny manager is personally scheduling every enzyme, which is probably for the best. The paperwork would be impossible. The beating heart, the breathing lungs, the sleeping brain, the adapting immune system, and the shifting hormones all show that life is not a static state. It is a process. A living organism is never simply the same from one moment to the next. It renews, repairs, responds, and changes. And because it changes through interacting rules, feedback, and sensitivity, it can show the same kind of rich behavior we have seen elsewhere in chaos theory. This makes the body feel less separate from the rest of nature. The branching of blood vessels echoes rivers and trees. The electrical activity of the brain echoes waves and storms in a very different medium. The heartbeat carries variation like a rhythm in flowing water. Breath rises and falls like a tide. The body is not a sealed machine dropped into the universe. It is part of the universe, using the same principles of pattern, feedback, flow, and adaptation that appear everywhere. There is comfort in that, especially when listening at night. Your body does not need to become perfectly still in order to rest. It only needs to move into gentler patterns. The heart slows. Breathing deepens or softens. Brain rhythms shift, muscles loosen, hormones change, temperature drifts. Sleep arrives not as a switch, but as a transition through states. The body finds its way, as living systems do, by adjusting. And perhaps this helps us think about calm differently. Calm is not the absence of all change. It is a stable pattern of change. It is the nervous system finding a safer rhythm. It is breath and heart becoming better coordinated. It is the brain moving away from urgent loops and toward rest. It is not nothing happening. It is many things happening more quietly. Chaos theory, when brought into biology, does not make the body seem chaotic in a frightening way. It makes it seem intelligent in a distributed, physical, living way. It shows that health is often flexibility. It shows that variation can be a sign of resilience. It shows that strict regularity is not always the goal. Life needs room to move. Still, the word chaos can confuse us here. If someone says the heart is chaotic, we might imagine danger. If someone says the brain is chaotic, we might imagine disorder. But scientific chaos is not the same as ordinary chaos. A chaotic system can follow rules. It can have patterns. It can remain bounded. It can be sensitive and structured at the same time. The body uses this kind of dynamic complexity not as a flaw, but as part of being alive. And that leads us naturally to one of the most important clarifications in this whole story. Chaos is often mistaken for randomness. The two can look similar from the outside because both can be hard to predict. But they are not the same. A random system has no hidden deterministic path in the same way. A chaotic system may be deeply rule-based, yet unpredictable because of sensitivity. To understand chaos properly, we have to separate wildness from randomness and see why the difference changes everything. At first glance, chaos and randomness can look like close relatives. They both refuse to sit neatly in a chair. They both make prediction difficult. They both give the impression that something has slipped beyond our control. A storm changes direction. A heart rhythm varies from beat to beat. Smoke curls upward in a way no one could draw twice. A crowd shifts, traffic slows, a flame flickers, and the pattern seems to say, "Good luck trying to guess what I will do next." So it is understandable that we often use the words as if they mean the same thing. If a room is messy, we call it chaotic. If a plan falls apart, we call it chaos. If the weather changes 3 times before lunch, we may call it random, especially if we are holding the wrong coat. In everyday speech, the difference does not always matter. Both words point toward disorder, uncertainty, and that familiar feeling that the universe has once again misplaced the instruction manual. But in science, chaos and randomness are not the same. They may look similar from a distance, but up close they belong to different kinds of uncertainty. Randomness means that there is no exact deterministic pattern behind the individual outcome, or at least no pattern available in the way the process is defined. Chaos means something more subtle. A chaotic system can follow precise rules. It can be fully cause and effect. It can be deterministic, meaning the next state comes from the previous state according to the system's rules. Yet it can still be impossible to predict in detail over long periods because tiny differences in the starting point grow rapidly. That is the heart of the distinction. Randomness is uncertainty without a fixed path. Chaos is a fixed path that becomes impossible to follow unless you know the beginning with impossible precision. Imagine rolling a die. You shake it in your hand, let it tumble across the table, and it comes to rest showing one face. In ordinary life, we call this random. In a deeper physical sense, the die follows laws of motion as it bounces, spins, collides with the table, and slows. If you knew every detail of the throw, the exact position of the die, the force of your hand, the texture of the table, the tiny air currents, the bounce, the rotation, the friction, then perhaps in principle you could predict the outcome. But in practice, the system is so sensitive that the result behaves like randomness. A tiny difference in how the die leaves your fingers can change the final face. So even this simple example sits near the border. What we call random in daily life may sometimes be chaotic motion hiding behind practical ignorance. Now compare that with a truly random process, such as the way certain quantum events are understood in modern physics. If a radioactive atom decays at a particular moment, we can predict the probability over time, but not the exact moment for one individual atom in the same deterministic way as a clock gear turning. At least according to standard quantum theory, the individual event is not merely hard to predict because we lack enough detail. It has an intrinsic probabilistic character. This is different from a chaotic system, where the future is determined by the present, but our inability to measure the present perfectly destroys long-term prediction. That difference may sound small, but it changes everything. A chaotic system is like a story written in ink so fine that you cannot read all the letters. The story is there, and it follows from one line to the next, but your eyes cannot catch enough detail to know where it is going. A random system is more like a page where the next word is chosen according to chance. Both leave you uncertain. But the reason for the uncertainty is not the same. This is why the phrase deterministic chaos is so important. It sounds contradictory at first. Deterministic suggests strict cause and effect. Chaos suggests wild unpredictability. Put them together, and the mind raises an eyebrow. How can something be both? But this combination is exactly what chaos theory revealed. A system can be governed by definite rules, and still be unpredictable in practice because of sensitive dependence on initial conditions. The double pendulum is a good example. It is not random. The rods, joints, gravity, and motion obey physical laws. If you started in exactly the same position with exactly the same motion, it will follow exactly the same path, but start it almost the same way, with a difference too small for the eye to notice, and after a while the motion may look completely different. The system has not become random. It has amplified a tiny difference. It is deterministic but sensitive. Weather works in the same way. Tomorrow's weather does not arrive by pulling names from a hat. The atmosphere follows physics. Heat, pressure, moisture, wind, sunlight, and Earth's rotation all interact according to rules. But because the atmosphere is chaotic, small uncertainties in the present grow with time. The forecast becomes less exact the farther ahead we look. The atmosphere is not random in the same way a coin toss is often treated as random. It is a vast deterministic system with limited predictability. A useful way to feel the difference is to imagine two kinds of unknown music. In the first, a musician is improvising. The melody changes, wanders, surprises you, and never repeats exactly. But if you listen carefully, you hear structure. The musician returns to certain themes. There is rhythm, style, memory, and response. The song is unpredictable, but not meaningless. That is chaos. In the second, notes are produced by pure chance, with no memory of what came before and no rule linking one note to the next. That is randomness. Both may surprise you. Only one carries the hidden shape of a system unfolding. Of course, real systems can mix both. Nature is not always kind enough to put neat labels on things. A weather model may be chaotic, but measurements also contain noise. A heart rhythm may have deterministic patterns, but also random fluctuations. A market may contain feedback, human choices, external shocks, and uncertain events all at once. Many real systems combine chaos and randomness, structure and noise, rule and chance. Part of the challenge is learning how to tell which kind of uncertainty is present. This is not always easy. If you only look briefly, chaos can look random. A chaotic signal may seem irregular, jagged, and unpredictable. But if you observe longer, analyze carefully, and look for patterns in the right way, hidden structure may appear. The motion may stay within certain bounds. It may return near earlier states. It may form an attractor. It may show sensitivity to starting conditions. Randomness, by contrast, does not create the same kind of deterministic structure. though random systems can have statistical patterns. Statistics gives us one way to study randomness. If you flip a fair coin once, no one can say with certainty how it will land. But if you flip it many times, the overall pattern becomes predictable in a statistical sense. You expect roughly balanced outcomes over a large number of flips. The individual event is uncertain, but the distribution is stable. Randomness can have reliable averages. Chaos can also have reliable averages, but its structure comes from a different source. A chaotic system may wander unpredictably through its possible states, yet stay within an attractor. It may produce long-term patterns, frequencies, and tendencies. The exact path is hard to predict, but the overall region of behavior can be studied. So both randomness and chaos can be described statistically, but chaos has an underlying rule-based unfolding that randomness does not necessarily have. Imagine watching leaves fall from a tree on a breezy day. One leaf spins left, another flips right, another drifts down in a slow spiral. The paths look random, but each leaf is shaped by gravity, air resistance, turbulence, shape, weight, moisture, and the wind around it. The motion may be chaotic because tiny differences in air currents and leaf orientation grow into different paths. If a gust arrives, everything changes. The falling leaves are not simply choosing at random. They are physical objects moving through a sensitive environment. Now imagine drawing numbers from a bag where each number is equally likely, and the draw is not influenced by previous draws once the number is returned. That is a more straightforward random process. The next number does not remember the previous one. It is not pulled toward an attractor by deterministic motion. It is chance according to a defined probability. Memory is another clue. Chaotic systems often carry a kind of memory through their present state. The next moment depends on the current moment, and the current moment contains the influence of earlier moments. A river's next swirl depends on the flow already shaped by rocks, banks, and previous turbulence. A population's next change depends on its current size, food supply, predators, and past growth. A heart's next beat depends on ongoing signals in the body. The past is folded into the present. Random processes, depending on the kind, may have little or no memory. A simple coin flip does not care what happened last time. It does not feel embarrassed about landing heads 5 times in a row and decide to make things fair. It has no mood, no guilt, and no long-term plan, which makes it emotionally healthier than some group chats. Each flip is independent in the ideal case. Chaos, by contrast, is often deeply dependent on history. This is why chaotic systems can be so hard to reset exactly. To recreate the same future, you must recreate the same present, and the same present may require details beyond reach. If you stir cream into coffee, the pattern that forms depends on the exact motion of the spoon, the temperature, the shape of the cup, the thickness of the cream, tiny currents in the liquid, and what happened the moment before. Try to repeat it, and you will create something similar but not identical. It is not random, but it is unreproducible in exact detail. The difference between similar and identical matters in chaos theory. In ordinary life, similar is usually enough. If 2 cups of coffee taste nearly the same, we are content. If 2 walks follow nearly the same route, we call them the same walk. If 2 mornings begin with the same alarm and the same sleepy search for slippers, we do not demand philosophical precision. But chaotic systems care about small differences. Similar beginnings may not stay similar. Over time, they can separate. This is also why chaos does not mean anything can happen. That is another common misunderstanding. A chaotic system is not unlimited. It is not free in the way pure imagination is free. The double pendulum will not suddenly become a tulip. The weather will not produce a snowstorm in a hot oven. A river will not flow uphill just because it is feeling experimental. Chaotic systems are constrained by their rules, energy, materials, and conditions. Their unpredictability exists within boundaries. A strange attractor is one way those boundaries appear. The system may move unpredictably, but it remains within a certain pattern of motion. This is very different from pure randomness spread evenly over all possibilities. Chaos has shape. Randomness may have distribution. Both can be studied, but they ask for different questions. If we mistake chaos for randomness, we may miss the structure. We may look at an irregular heartbeat and see only noise when the pattern of variation contains information. We may look at climate variability and confuse short-term weather chaos with long-term physical trends. We may look at a complex ecosystem and assume its changes are arbitrary, when feedback loops and thresholds are guiding it. The distinction matters because it affects how we understand, predict, and respond. In medicine, for instance, recognizing meaningful variability can be important. A signal from the body may look messy, but that messiness may contain structure. Heart rate variability, brain activity, gait patterns, and sleep rhythms can all carry information about health. If every irregularity were dismissed as random noise, valuable clues could be lost. At the same time, if every irregularity were treated as meaningful, we would see patterns where none exist. Science has to walk carefully between those mistakes. This careful walking is also important in daily thinking. Human beings are pattern-seeking creatures. We are very good at noticing connections, sometimes too good. We see faces in clouds, messages in coincidences, and grand destiny in the fact that the same song played twice in 1 week. This tendency can be charming, but it can also mislead us. Chaos theory does not mean every small event has a meaningful hidden purpose. It means that in certain systems, small differences can grow through lawful interactions. That is different from saying every coincidence is a secret message. A butterfly may influence the atmosphere under some conditions, but that does not mean the butterfly intended the storm. A missed train may lead to an important encounter, but that does not mean the universe arranged the timetable personally. Chaos gives us a science of sensitivity, not a guarantee of fate. This distinction keeps the subject honest. It prevents chaos theory from becoming a vague cloud of dramatic statements. The real idea is strong enough without exaggeration. Systems can be deterministic and unpredictable. Small uncertainties can grow. Simple rules can produce complex outcomes. Hidden structure can exist inside irregular motion. That is already remarkable. We do not need to add mystery where the science is already full of wonder. The difference between chaos and randomness also changes how we think about control. If something is truly random, control may mean working with probabilities. If something is chaotic, control may mean identifying sensitive points, stabilizing feedback, or guiding the system into a desired region. In some chaotic systems, small interventions can have large effects if applied at the right time and place. That is because the system is sensitive. A tiny push at the right moment can shift the path. A tiny push at the wrong moment may do almost nothing. This is familiar in ordinary life too. Sometimes a small change in routine can stabilize a day. Going to bed a little earlier, taking a walk before stress builds, answering a difficult message before it becomes a mountain. Moving one cup away from the edge of the table before it begins its tragic journey to the carpet. These are not grand acts, but in sensitive systems, timing matters. A small action can matter when it enters a loop. In engineering and science, controlling chaos has become a real field of study. Researchers have explored ways to stabilize chaotic systems by making small adjustments. The goal is not always to crush chaos completely. Sometimes the goal is to keep useful flexibility while preventing harmful instability. This is especially important because chaotic behavior is not always bad. In some contexts, variation and sensitivity allow adaptation, exploration, and resilience. The problem is not chaos itself. The problem is chaos in the wrong place at the wrong scale without enough stability around it. The body again gives us the lesson. Too much rigid order is unhealthy. Too much uncontrolled disorder is unhealthy. Between them lies dynamic balance. The same is true in many systems. A forest needs disturbance, but not constant destruction. A brain needs flexibility, but not disorganization. A society needs structure, but also the ability to adapt. Even creativity often lives between order and surprise. A piece of music that is completely predictable may become dull. A piece that is completely random may become noise. The sweet place is often where pattern meets variation. Chaos theory helps us see that this middle space is not a failure. It is a rich and important region. It is where many living and natural systems do their most interesting work. Randomness, meanwhile, has its own importance. Random variation is essential in evolution. Random sampling helps science. Randomness is useful in computing, games, security, and statistics. It is not lesser than chaos. It is simply different. Both belong to the universe. Both shape what can be known. Both challenge prediction, but they challenge it in different ways. One of the simplest ways to remember the difference is this. Randomness has uncertainty because the outcome is not fixed by a knowable deterministic path in the same way. Chaos has uncertainty because the path is fixed, but too sensitive to follow far ahead. Randomness is like drawing from a cloud of possibilities. Chaos is like following a thread that twists so finely that a tiny mistake in your grip sends you to a different part of the knot. That thread image brings us back to the larger story. Chaos theory did not destroy the idea of order, it expanded it. It showed that order can be hidden inside irregularity. It showed that prediction can fail even when rules remain. It showed that the world may be neither a perfectly predictable machine nor a meaningless roll of dice. It is often something in between, lawful and sensitive, patterned and surprising. This middle vision may be the most important gift of chaos theory. It rescues us from two extremes. On one side is the old dream that everything can be predicted exactly if only we know enough. On the other side is the despairing idea that everything is random and nothing can be understood. Chaos theory says no to both. It says the universe can be deeply understandable and still not fully predictable. It says uncertainty does not always mean ignorance. Sometimes uncertainty is a feature of the way lawful systems unfold. That is a very different way to see reality. It is humbler, but not hopeless. It's less controlling, but more attentive. It asks us to look for patterns without demanding perfect certainty. It asks us to respect small beginnings without imagining that every small thing is destiny. It asks us to notice feedback, sensitivity, limits, and hidden shapes. It asks us to become better listeners to systems that do not speak in straight lines. And perhaps this is why chaos theory has such a lasting hold on the imagination. It feels scientifically precise and emotionally familiar at the same time. We live in a world that is not random, yet not fully predictable. Our bodies, weather, thoughts, relationships, ecosystems, and histories all unfold through causes too tangled to fully trace. We understand some patterns, we miss others, we plan, adapt, revise, and keep moving. The difference between chaos and randomness helps us see this without confusion. It gives us a language for the kind of uncertainty that belongs to complex order. A storm is not a dice roll, a heartbeat is not static, a life is not a machine. The world is full of systems that obey rules while still surprising us, and that surprise is not a flaw in the rules. It is what happens when rules are allowed to grow, loop, fold, and respond. So when we say chaos is not randomness, we are saying something quietly profound. The unpredictable may still have causes, the irregular may still have structure, the unknown may still be shaped, and the universe, even when it refuses to tell us exactly what comes next, may still be inviting us to understand the deeper patterns of how change happens. From here, the last step is to widen the view again, away from the die, the pendulum, the storm, and the heartbeat, and ask what chaos theory really reveals about the universe itself, and about our place inside a reality that is ordered, sensitive, and forever unfolding. By the time chaos theory has carried us through weather, butterflies, strange attractors, fractals, living bodies, and the difference between chaos and randomness, it begins to feel less like one narrow scientific subject and more like a change in eyesight. The world has not changed, of course. Clouds still gather, rivers still bend, hearts still beat. Leaves still tremble in small winds. But once the idea of chaos settles into the mind, the familiar world becomes deeper. Motion that once looked messy may now seem patterned. Predictability that once seemed obvious may now seem fragile. Small beginnings, once easy to ignore, may now feel quietly important. Chaos theory reveals that the universe is not as simple as a clock and not as careless as a dice roll. It lives somewhere more interesting than either picture. It follows laws, but those laws can create surprise. It contains order, but that order can be sensitive. It produces patterns, but those patterns may never repeat exactly. The old dream of science imagined that if we knew enough, we could calculate everything with perfect certainty. Chaos theory did not throw away science. It made science more honest. It showed that even in a rule-governed universe, there can be limits to prediction. Not because reality is irrational, but because reality is wonderfully, stubbornly, richly connected. That may be the first great lesson. The universe is lawful, but not always predictable. This is a subtle distinction, and it matters. If a system is lawless, then science has no grip on it. But chaotic systems are not lawless. A double pendulum follows physical rules. The atmosphere follows physical rules. A river follows gravity, friction, pressure, and the shape of the land. A heartbeat follows electrical signals, muscle contraction, hormones, and nervous system feedback. These systems are not doing whatever they like. They are not breaking nature's rules. They are showing us what nature's rules can do when they interact, repeat, feedback, and amplify small differences. This means unpredictability is not always a sign of ignorance. Sometimes it is a feature of the system itself. We may know the rules and still be unable to predict exact details far into the future, because we cannot know the starting conditions with perfect precision. A tiny uncertainty today becomes a larger uncertainty tomorrow, and a larger one after that. The future is not disconnected from the present. It is too delicately connected to be followed perfectly. There is something humbling in that. Science often begins with the human desire to understand and predict. We want to know when the storm will arrive, how a disease will progress, whether an ecosystem is stable, where a spacecraft will travel, how a market might behave, and what the climate will do over decades. We are not wrong to ask. Prediction is useful. It saves lives. It builds bridges. It guides decisions. But chaos theory says, ask carefully. Some systems will answer with exactness for a while, then with probabilities, then with broad tendencies, and eventually with silence about the fine details. The silence is not failure. It is part of the truth. That truth changes how we think about knowledge. In a perfectly predictable world, knowledge would mean knowing the future exactly. In a chaotic world, knowledge often means understanding patterns, limits, ranges, tendencies, and sensitive points. We may not know the exact path of every swirl in a river, but we can understand the river's flow. We may not know the precise shape of every cloud tomorrow afternoon, but we can understand the atmosphere's behaviour. We may not know every future turn in a life, but we can understand that habits, feedback, environments, and small repeated choices shape what becomes possible. Chaos theory teaches us to trade the fantasy of total control for the deeper skill of attentive understanding. This second lesson is that small things can matter, but not in a simple fairy tale way. The butterfly effect is often repeated as if every tiny action must lead to some enormous consequence, but the real idea is more careful. In sensitive systems, small differences can grow. They do not always grow. Many small disturbances fade away. A butterfly wing may vanish into the background air. A tiny ripple may disappear before reaching the shore. A small mistake may be corrected before it spreads. But under the right conditions, when a system is poised, connected, and sensitive, small differences can become large ones. This is true in weather, but also in many other systems. A slight change in temperature can shift whether ice melts or remains. A small delay in traffic can become a slowing wave through hundreds of cars. A minor imbalance in an ecosystem can grow if feedback reinforces it. A small change in sleep or stress can affect mood, and mood can affect choices, and choices can affect the next day. Again, chaos theory is not fortune-telling. It does not say every detail is destiny. It says the world contains systems where beginnings matter, because they are amplified through interaction. That lesson can make us gentler with the present. We do not have to believe we control everything in order to believe our actions matter. A kind word may not change the world, but in the right moment, it may change the direction of someone's day. A small repair in a habit may not transform a life overnight, but repeated through feedback, it may alter the pattern. A small environmental change may help stabilize a fragile system. Small does not mean powerless. It only means its power depends on the system it enters. The third lesson is that complexity does not always require complicated causes. This may be one of the most astonishing ideas in all of modern science. Simple rules can create wild worlds. A few repeated instructions can produce branching patterns, irregular rhythms, spirals, cycles, and motion that never repeats. A flock of birds can move with grace because each bird follows local responses. A tree grows its branching form by repeating growth rules under changing conditions. A river carves a complex network by flowing downhill through varied land. A snowflake builds delicate structure through the repeated attachment of water molecules under changing air. The universe is creative with repetition. It does not need to design every detail in advance. It can grow details through process. This is why chaos theory and fractals feel so closely connected. Fractals show how repeated patterns can appear at different scales. Branches within branches, curves within curves, roughness within roughness. They reveal that nature often builds richness through the same idea repeated with variation. The world is not a flat surface with decoration added. It is layered, nested, and alive with scale. This helps explain why the natural world feels so different from human-made smoothness. A perfect circle is elegant, but a cloud is not a circle. A straight line is useful, but a coastline is not straight. A polished sphere is simple, but a mountain is ridged, cracked, rough, and full of smaller forms. Nature's shapes are often irregular because they are shaped by history. Wind, growth, erosion, stress, flow, heat, and time leave traces. A fractal pattern is not just a shape, it is the visible memory of a process. The fourth lesson is that chaos can have hidden structure. This is the gift of strange attractors. At first, chaotic motion seems to wander without plan, but when we look in the right way, the motion may reveal a shape. It may remain within boundaries. It may return near earlier states without repeating. It may trace a pattern through possibility space, not a simple loop, not a resting point, but a folded, layered form. This means chaos is not the same as meaningless disorder. It can be structured unpredictability. That idea has emotional weight, even if we keep it grounded in science. Many things in life feel irregular from moment to moment. Thoughts return, but never the same way. Days repeat, but never exactly. Sleep comes in cycles, but each night is different. Relationships, moods, routines, worries, and hopes all have patterns without perfect repetition. Life is not random, and it is not fully predictable. It moves through habits, feedback, memories, and changing conditions. It has attractors of its own, not in the strict mathematical sense every time, but in the sense that systems return to familiar regions. A person may return to certain thoughts when tired. A family may return to certain conversations. A city may return to traffic patterns. An ecosystem may return to balance after disturbance, until one day the disturbance is too much and it shifts. A body may return to health, or settle into illness, depending on feedback, resilience, and conditions. Strange attractors give us a way to imagine how systems can wander without being free of structure. They teach us to look for the shape of motion, not only the position of a thing at one instant. The fifth lesson is that stability is often active. This is especially clear in living systems. A healthy body is not still in the sense of being unchanging. It is stable because it changes well. Heart rhythm varies, breathing adjusts, hormones rise and fall, brain activity shift through states, temperature regulation, immune responses, digestion, balance, and sleep all depend on feedback. Life is maintained by motion. The body is not a statue, it is a living negotiation. This changes how we think about order. Perfect regularity is not always health. A heart should not be wildly uncontrolled, but neither should it behave like a lifeless metronome. A brain needs coordination, but too much rigid synchronization can be harmful. An ecosystem needs structure, but also flexibility. A society needs rules, but also adaptation. Across many systems, resilience often lives between stiffness and breakdown. Too much order becomes brittle. Too much chaos becomes dangerous. The richest zone is often between them, where patterns can hold together while still responding to change. This middle space may be one of the deepest things chaos theory reveals. The universe is not divided neatly into order and disorder. Many of its most important systems live between those extremes. A flame flickers there. A brain thinks there. A forest grows there. Weather forms there. A heartbeat rests there. Creativity often lives there too, where ideas are structured enough to make sense but loose enough to surprise us. Music, conversation, dreams, and thought all need both pattern and variation. A lullaby is not one note forever. It moves, but gently. It changes, but within a calming form. The sixth lesson is that uncertainty is not always the enemy. This may be the hardest lesson, because human minds like certainty. We want the future organized before we enter it. We want to know what will happen, when, and why. We want clear lines between cause and effect. We want tomorrow to hold still while we prepare for it. But in a chaotic universe, some uncertainty remains no matter how carefully we measure. That does not make knowledge useless. It makes humility necessary. Humility in science is not weakness. It is a strength. It means being precise about what can be known, what can be estimated, and what cannot be predicted exactly. Weather forecasts use probabilities. Climate science studies long-term patterns. Medicine studies risk and response. Ecology studies stability and thresholds. Engineers design systems with safety margins. Good understanding does not always mean perfect prediction. Often, it means knowing how uncertainty behaves. This is not only a scientific lesson, it is also a practical one. If the future is sensitive, flexible, and partly unpredictable, then rigid plans may fail. Systems need adaptation. We need feedback. We need to pay attention to what is happening now, not only what we expected to happen. A sailor cannot control the wind, but can learn to read it. A gardener cannot command the weather, but can prepare soil, choose plants, and respond to conditions. A physician cannot reduce the body to one variable, but can monitor patterns and guide balance. A person cannot know every future turn, but can cultivate habits that make better futures more likely. Chaos theory does not tell us to give up control and drift helplessly. It tells us to replace control with participation. We are inside systems, not outside them. We are inside weather, biology, society, memory, and time. We influence and are influenced. We act, observe, adjust, and act again. That is how living beings move through a sensitive world. The seventh lesson is that the universe is connected across scales. A small air current can become part of a larger pattern. A tiny stream can feed a river. A cell signal can affect an organ. A local rule can create a global shape. A short-term fluctuation can be part of a long-term trend. Chaos theory and fractals both encourage us to look between scales, not only at one level. The very small and the very large are not always separate. They are linked through feedback, branching, flow, and repeated structure. This is one reason the world feels so woven together. The atmosphere connects ocean and land. Rivers connect mountains to seas. Plants connect sunlight to soil. Bodies connect breath to blood to brain. Ecosystems connect insects, roots, fungi, animals, water, and climate. The universe is not a pile of isolated objects. It is a web of processes. Chaos theory does not invent that web. It helps us see how sensitive and dynamic the web can be. And perhaps this is why chaos theory has become so powerful outside physics and mathematics. It speaks to weather, biology, medicine, ecology, engineering, astronomy, economics, and even the way we think about human life. It must be used carefully because not everything complicated is automatically chaotic, and not every irregular pattern has a deep hidden meaning. But when used well, it offers a language for systems that are lawful, non-linear, sensitive, and rich. It reveals a universe where prediction is possible, but bounded, where order exists but can be flexible, where small things may matter, but only through the structure of the system, where randomness and chaos are not the same, where patterns can hide inside irregularity, where roughness is not failure, where the same principles can echo through clouds, coastlines, arteries, rivers, flames, and thought. So what is chaos theory really? It is not just the butterfly effect, though the butterfly gave it a memorable pair of wings. It is not just weather prediction, though weather helped open the door. It is not just strange attractors or fractals or sensitive beginnings. It is a new way of understanding how change unfolds in systems, where everything affects everything else. It is the science of patterned unpredictability. It is the study of how simple rules can become complex, how order can become unstable, how motion can draw hidden shapes, and how uncertainty can arise without breaking the laws of nature. It teaches us that the universe is not a machine with every future gear easily visible. It is also not a meaningless storm. It is more like a vast set of flowing patterns, some stable, some sensitive, some repeating, some branching, some folding back on themselves. It is a universe where rivers carve landscapes, clouds build and dissolve, stars move in gravitational dances, cells coordinate into bodies, and minds wake each day into futures that are shaped but not fully written. There is something peaceful in this, if we let it be peaceful. Chaos does not have to mean panic. It can mean that life is flexible. It can mean that the future has room. It can mean that small acts of care may matter in ways we cannot fully measure. It can mean that uncertainty is not emptiness, but openness within law. It can mean that the world is understandable without being exhausted by our understanding. And now, as this quiet journey nears its resting place, perhaps the idea of chaos feels a little different from when we began. Not a mess, not a collapse, not the universe losing its mind. Chaos is the trembling edge of order, the sensitive unfolding of rules, the hidden shape inside motion. It is the reason a cloud is never the same twice, the reason a river keeps finding new curves, the reason a heartbeat is alive with small variations, the reason weather can be studied and still surprise us. Somewhere outside, air is moving in delicate layers. Somewhere, water is finding a path through stone. Somewhere, a branch is growing toward light, dividing into smaller branches, and those into smaller still. Inside you, breath rises and falls, the heart adjusts, the brain drifts through changing patterns, and the body keeps its quiet balance through motion. None of it is perfectly still. None of it is perfectly predictable, and yet it holds together. Maybe that is what chaos theory really reveals about the universe. Not that everything is out of control, but that control was never the deepest kind of order. The deeper order is dynamic. It moves, it responds, it folds small beginnings into larger patterns. It lets the future grow from the present without making the future simple. It gives nature room to be lawful and surprising at the same time. So wherever you are listening from and whatever small changes shaped your day, you are part of a universe that is still unfolding. A universe of rhythms and branches, storms and stillness, feedback and rest. A universe where certainty has limits, but wonder does not. And in this moment, with the noise of the day softening and the mind beginning to loosen its grip, perhaps it is enough simply to breathe with the pattern. Let the unknown remain gentle and drift quietly inside the strange, ordered, beautiful motion of it all.